Store. And we are now recording. We go from current slide. It'll get there one of these days, I guess. There we go. And before we actually start, we go over just a couple of announcements. One is something I've seen on the board, on the walls. I probably got it in an email, but I haven't found it there yet. It sounds like a very nice program coming up Friday morning at 9:30 on the Birmingham East Campus. It's in the A.G. Gaston Auditorium, which is a nice auditorium if you haven't been there. A UAB traveling company, they have a name, I can't, theater company or something like that, is going to be doing Broadway hits, and there will be, it's a musical production for many of the, I guess, fairly recent Broadway productions, and it should be quite good. I know there are a bunch of pretty talented people. I'm almost wondering if some of Lawson's former students might not be in it, but they may not be, I don't know. But I wouldn't be at all surprised because I know we have a pretty good relationship with UAB. But anyway, it's, yeah.
I was about to say, UAB's guys are coming over to the East Campus on Friday. I mean,
yeah, that's right.
It's a shame I won't be able to make it because I'll be over here at work.
Oh, I see. Okay.
Yeah, work stuff.
Yeah. Well, it should be quite good. So if you can, try to make it. Other things that are on the things that I think are stuff you've already heard before. If you are getting close to graduating, if you're graduating in the spring, this is the best time to start the process for graduation application. You're not quite ready to get it completed yet, but you can at least start the process. Getting your degree plan together, getting with your advisor to go over that degree plan, see what you have taken, what you're currently taking, and what you still need to take to finish. So do that. If you're not graduating in the spring, remember to do it the term before you graduate, okay? That way you can schedule the courses you need to guarantee you'll be graduating on time. And even if you can't get them all scheduled, maybe you can work with somebody to get them to add a class or something like that, or do a class substitution. It's good to get that kind of stuff done before the fact rather than trying to, panicking right at the end saying, I got to have this course and I can't get it this term. What do I do? So start that process the term before you graduate. Okay? Number two, they are looking for note takers. I know on the Birmingham campus, perhaps this campus as well, it's a really good opportunity to do something really good for someone who needs the help, and they pay you, so it's a win-win. And then they're also looking for peer tutors in math, biology, English, computer science, and Spanish. So if any of those are your bag, you might try the Space Center. On this campus, we also have tutoring in student support services. So there's two places on this campus, one on the other, that you can probably do that. And again, you're helping someone, but guess what? When you're tutoring someone, you're improving your knowledge of that too. And so you're helping yourself, and you get paid for it. So a win-win-win situation there. So please consider doing that. All right, so let's look at, well, let me pause just for a moment here. I hate to do this, but I'm going to. Here we go. I wanted to check one thing before I say anything else. I emailed Jerry Tracy, and I meant to before I came to class to check that, but like I said, that student came by for an interview, and no, I don't have an answer yet. Okay, so I wanted to check to tell you, but all right, let's go back to this. All right, where are we going from here? We will finish, knock on wood, chapter 23 today. It shouldn't take us very long. There's only a couple more slides, few other things to talk about, so we'll be through with Chapter 23. The lab for 23 is the visit to the Channel 13 Weather Center, okay, with Jerry Tracy or Harmony Mendoza or whoever is on duty that day. So I did, like I said, I emailed Jerry to see if and when we might be able to go. And since Chris is here, we can continue, okay? So I'm hoping to get an answer today. So far not, but I hope that we'll get one today, or at least by Thursday, so I can tell you then. If we get it, if I get it today or tomorrow and they say come Thursday, then I'll be contacting you via email, Blackboard. They'll send you an email as well as posting an announcement. So be watching for that between now and Thursday, okay? I'm guessing if he hasn't sent anything today, it'll probably be next week. But I told him it's got to be Thursday, Tuesday, or Thursday of next week, and that's all, folks, because that's all we have. And we can do it even the last day of class. We'll manage to work things out, either taking the final early or taking the final when we get back from the field trip or something like that. So we'll manage to conclude that if he does say Thursday is the only day we can. Now, this past summer, I tried weeks ahead of time, a couple weeks ahead of time, and just kept failing to get them. And finally got a response that said, can you come today? And that was the day of the final exam. I didn't have the vehicle lined up or anything else. I said, no, we just can't do it today. So hopefully this time there'll be enough time for him to respond and we can get things worked out. So that's going to be our lab for today. And since we will finish the chapter today, then we will have the test on Chapter 23 on Thursday. Last 30 minutes of class on Thursday. All right, we will, after we finish the chapter today, we're going to get started on Chapter 24. Yes? Absolutely. That's a fascinating subject. You may even want to narrow it down some, but yeah, that was. Yes. That would be incredible. Yeah, very good choice. Okay. So today we'll finish 23. We'll start on 24. Thursday. Well, from now on, we're going to try to make the field trip whenever we can, and if we don't make the field trip on Thursday, then we'll continue Chapter 24. Possibly finish it on Thursday. If not, definitely finish it on Tuesday. Believe we will. And if we don't finish it until Tuesday, that means we will have on Thursday, when you do your final, we'll actually do two tests, the last chapter test and the final exam. If we finish it, say Thursday, then we can have the Chapter 24 test on Tuesday and the final on Thursday. Okay. There will be a lab for Chapter 24, but it's an in-class lab. It's a paper lab. You'll just use, I've got a series of things for you to look up in the text. That's all you'll need is a text and go through it and find that there. So that will be, and that will take us pretty much through Tuesday of next week. Unless the field trip is Thursday or the field trip has come along and bunched other stuff up, I think we'll have plenty of time on Thursday of next week, final exam day, to have the final, either the Chapter 24 test and the final or just the final, and probably have time for a pizza party if you want it. Would that be favorable or not?
Oh, it would be favorable.
Okay, well, we'll talk about that next Tuesday, by next Tuesday anyway. Now, if it turns out that we actually go to Channel 13 on next Thursday, then we'll talk about whether we'll come back here and have the pizza or maybe stop somewhere on the way and have something, or pizza or something else. So we'll fiddle about that next week as we know more. And remind me before the end of class today, check my email again and see if Jerry has answered during class. He may have, because it's about the time he normally goes into work. All right, any questions before we get started today? We've had tests on every chapter now that we've covered, so we're up to date on our test. We got chapter 23 and 24 to go, final exam to go. The trip to the Weather Center will be chapter 23 lab. The lab for 24 will be an in-class, pretty simple lab to do. All right, now, while I'm on that subject, sore subject, your papers. I think I've said before, I've got 5 in out of, I think we're down to 14 students now. That's barely more than a third of the class. We've only got this week and next week to go, folks, and I don't want the papers coming in on Thursday of next week. So basically you got today, or you got the rest of this week, and then Monday, Tuesday, and Wednesday of the following week. I'd rather have them by Tuesday rather than waiting till Wednesday, but get them in, okay? Now, I've done this just about every time. Labs. In the first lab, I'm still missing 1 lab, okay? First test. Still missing 1. He's not here right now. Second lab. It looks like maybe I have gotten all those in. So I'm going to return your second labs to you today. I didn't anticipate that. I didn't know that had happened. Let me get Dante here before I do that. I would have already had these out there. But I guess the last one came in last week, and I didn't realize it was the last one. Okay? Someone just turned in one last Thursday. Make sure on this lab 2. Yes, it looks like all of them. The thing that's nope. Lab 2, 1 missing. Sorry, I thought I had it. No, still missing 1 on lab 2 too, so I can't return those to you today. I didn't think I did. Okay. All right. Test 2, missing 1. Lab 3, missing a bunch.
I turned mine in.
Yeah, okay, just got it. Okay, test 3, missing 1. Okay, not always the same person, by the way. Lab 4, missing 1, 2, 3. Test 4, missing 1. Lab 5, missing a bunch, not as big a bunch, but a bunch. Test 5, missing 1, 2, 3. Lab 6, missing 1. Test 6, missing a few, quite a few actually. Lab 7, well, Lab 7 was the trip to the planetarium. So you either were there or you weren't there. And all but one of you were there, which was real good to see. Lab 8, I've gotten maybe 5 of those in. Those are the ones we did last time. And test 7, I'm still grading it, so I'll get those caught up. So please, folks, I thought I could return something today, but I can't. Okay. Any questions then before we get going on today? All right, remember, this chapter is weather and climate. We've already covered weather, and now we're talking about climate. What's the difference? Anybody? What's the difference in weather and climate?
Climate is like, climate is only the years, weather is like.
Yes, that's a pretty good description of it. Weather is what's happening pretty much now, the current situations, that kind of stuff, whereas climate is over the long haul. And Darren is here. Okay. All right. Now, so we're talking about the major climate zones. We've talked about several ways to look at this. We've talked about by the globe, like tropical, temperate, and polar. Okay, that would be one way to look at it. Other ways of looking at it is what's the big influencers. That's sort of what this one is doing. Marine climates are those climates that are near the ocean. impacted largely by the ocean, influenced by the air masses coming from the oceans. Okay? Those would be your marine climates. Whereas your continental climate would be far from the oceans, so they're influenced mostly by air masses from large land areas. Now, if those land areas are to the north, generally that's going to keep you pretty cold. If those land areas are from the south, that could be hot and dry, okay? And it could be a combination. So those are your continental climates. Now, there are other classifications, sub-classifications. Now, I've just mentioned one. Very dry would be arid. Fairly dry, but a little more moisture, that would be semi-arid. What we live in, humid, okay? And then you have other classifications such as this as well, okay? So, let's take a look at a really detailed map, well, maybe a little complicated map of North America. Okay, and this will break down some of these major climate zones with subzones and sub-classifications. All right. Way up north, northern Alaska, northern Canada, and some of this dipped down pretty far south in Canada too. This is the polar region. Okay, basically dominated by cold. Okay. Ice, cold, frigid. Not too many people living there, not too much vegetation there. A fair number of animals really live there, and mostly having to do with water. Okay? Now, just south of there is humid continental. There's the continental. Okay? And I can't read that next word. Subarctic. Okay? Second. Subarctic. Still very cold, but fairly moist. And you see there's plenty of water on many sides of this, so it's not surprising it's somewhat humid. You may not get lots of rainfall, yes.
Which one is the most moist?
Which one?
Which one is the most moist?
Most moisture?
Moist, yes.
Okay, that would be humid. Okay? Now, this would be, it doesn't have to have lots of rainfall, but you see when it's so cold, you don't lose that much moisture to evaporation. So you keep a good amount of humidity there. And much of Alaska is that. Most of Canada is that. Okay? And maybe a little bit of the northern U.S., but really very little. Okay? Then the next one is humid. Continental, mid-latitudes. Humid, continental, subarctic, humid, continental, mid-latitudes. That would be right through here. This is southern Canada, northern U.S. now. Most of the Great Lakes area would be in this. Okay? And again, influenced largely by continental air. Mostly colder air coming down from the south, from the north, from the polar regions. Okay? Then we get into humid, continental, mid-latitudes, or what does that one say? Low latitudes. Okay? Now, I wouldn't call this exactly low latitudes. That's still mid-latitude to me, but it's the lower part of the mid-latitude. But I'd say that's even a stretch. Dimitri is here. Dimitri is the low line. Okay. Good deal. All right. Now, that's largely our Midwest. Okay? It's going, the southern part of the Great Plains are there. Most of New England would be up here in the one above it. Some of New England is here. Much of our farm belt is in this. It's humid, continental, and they call them low latitudes. But I think that's sort of a stretch to call them low latitude. Justin's here. Okay. Now, the next one here is humid subtropical. That's where we live, okay? We're right there, humid subtropical. Now look at this. This is pretty amazing. More than half of the U.S. is all considered humid. Now some of this is getting fairly dry out here to be called humid, but this up here can be classified humid because it's rather cool. It's not going to be so baked in the summertime, okay? This is humid, and most of this is humid because of the Gulf of Mexico, okay? Up here, Great Lakes and other areas, but down here, Gulf of Mexico. Notice people out here are dry, and we get most of our prevailing winds from the west. So you would think we would be dry. Gulf of Mexico pumps up the moisture. We are pretty fortunate to be in the situation we are. That's humid subtropical. And then tropical wet. Okay? Now they have a couple of these that are hard to distinguish. Okay? This is the tropical wet. That's this one right here. That's tropical. Not this. You can't classify anything in Alaska as tropical, okay? So this is not. This is over here, marine. This is the tropical wet down here. And I think that's the same in the book. Yeah. Okay? Now that's not even in the U.S. This is in the Yucatan Peninsula of Mexico. And many people might think of Mexico as being very dry, and much of it is not there. That is tropical wet. Okay? Then they have tropical with seasonally wet and dry, I think is what that says. Tropical with seasonally wet, dry. And that's the green down here. Right around the ocean, the Pacific Ocean here, and the Gulf of Mexico here, and extending down into South America. But it stays on either near bodies of water, but it's not always wet. And again, part of that is because the prevailing winds, and you see down here you're getting in the tropical areas, so you get western flow, east flow from the east and from the west, and in different seasons of the year, this mountain range that's in the middle here, that blocks the moisture from coming one way or the other. So therefore, it's seasonally wet, dry. Okay. Semi-arid. Oh my goodness, look, big chunk. Lots of Mexico, semi-arid. Desert Southwest here, semi-arid. Okay. Whole portions, and this is on the eastern side of the Rocky Mountains. The mountains over here have captured, blocked most of the moisture from going any further. You're out of range of the Gulf of Mexico, so this gives you the semi-arid environment there. Fairly dry. Some of this is still in the Great Plains, but the grasses will not be as dense and thick as it was with otherwise. Okay, I can't read that here. Desert. Okay, that's what I thought it was. These are just hot, dry deserts. Okay? And here, this is the strangest thing in the world to me. One of them, anyway. The Baja Peninsula of Mexico. This is called the Gulf of California here, even though none of it actually touches California. But this is the Baja Peninsula. Surrounded, totally surrounded by water, and it's a desert. Okay? And the fingers go up into this is the Mojave Desert in Arizona, California type area, maybe some of it into New Mexico. Very dry. And poor old Mexico, much of it, even though it's got water on both sides, very dry. Okay? Desert, in fact. Now, did anyone hear what's happening to these desert areas right about now? There's a tropical storm or a hurricane, or whatever the system is, coming up and going to blast the Yucatan Peninsula and the southwest desert areas. So New Mexico, Arizona, Southern California, Mexico, they're standing by, and they may get drenched. maybe as much as North Carolina and South Carolina got. And can you imagine that happening in the desert? North and South Carolina, plenty of grass, plenty of trees, plenty of soil cover, okay, to keep the soil in place. Desert areas, they aren't prepared for massive amounts of water. So they could literally be swamped. I mean, I would expect enormous land loss, soil loss, erosion. That's going to be happening there if they get pounded the way there's potential for them to happen. Okay, then they have the marine. Now this is interesting to call this marine. Now this certainly goes down into Northern California. Okay, Muir Woods is right here. If you get a chance to go to Central California, around the Bay Area, I know San Francisco, there's so much to see there. Go up to Muir Woods. I mean, it's just an incredible place. It's not a big touristy area, or it used to be anyway, but it's just an incredible sequoia trees. It's a beautiful area. And this is the Marine West. Of course, Portland and Seattle rains all the time. That's why it's a marine environment. Even in the Vancouver, this is British Victoria Island, Vancouver, all this area up in here. Even, and Juneau, Alaska is right in here, and this is all marine. Some of it quite cold. It doesn't mean it's warm, but it's just influenced mostly by moisture, by the ocean. Okay? But notice it doesn't get influenced like we do in the Gulf, because there's a mountain range right here, just inside, and that's what blocks the moisture from going any further, which makes the moisture concentrated right there. Okay, then you have the Mediterranean, and this is the San Francisco Bay Area, the wine country, Sausalito and Marin County, and then on down into central Florida. This is the Mediterranean climate. Okay, not anywhere close to the Mediterranean Sea, but still a Mediterranean environment. The entrees here. Okay. All right. Slowly we're filling up. And then we have the highlands. And you see, I mentioned the mountain range in Central America. It sort of forms the spine of the whole western part of the U.S., which, North America. Highlands here, highlands here, highlands here. This is Sierra Nevadas, the Cascades, and these are the Rockies. Okay, I don't know what the range is in Mexico. This is what creates so much of the desert-like environment there. Central America, that's what blocks the moisture coming east or west at certain times. Oh, and by the way, they mentioned Cuba. This is another name of it, I can't think. This is split between Haiti and Dominican Republic. Hispaniola, I think, is the island. Is that Puerto Rico? Yeah, I can't tell the islands from here, but but these are also tropical, seasonally wet dry. You would think they're surrounded by water to be always wet, but it's not necessarily. But even Hawaii is listed as tropical, seasonally wet dry. Now, I didn't know Hawaii was ever all that dry, but it may be certain, sort of monsoonal, okay? Not as bad as monsoon. So there's major climate zones. That doesn't mean every year, like this week, if they're getting pounded by moisture, that doesn't keep them from being a desert climate over the long haul. This week, the weather is not desert-like weather, okay? So you see, that's the difference in climate, one of the difference in climate and weather and climate. So let's look at, it says the following table, this is example 23, 3. Following table lists average monthly temperature data and total monthly precipitation data for a location in North America. Which major climate zone is this location? In which major climate zone? Now, these are temperatures in degrees Celsius. Anything that's negative is below freezing. Anything positive is above freezing. And look at this. The temperature ranged from negative 30 in February to only positive 7 in August. Well, 7 degrees would be close to 50 degrees, between 45 and 50 degrees. That's the average monthly temperature. Don't believe that's anywhere near us, okay? With average minus temperatures, meaning below freezing, 3, 6, 8 months of the year. That's not us, okay? So where would you guess that to be? And then look at the precipitation. In those cold months, hardly any. They're measured in millimeters, in fact. That's thicknesses of dimes now, okay? The month of April, 0 millimeters of rainfall on average in April, okay? 1 in February, 2 in January, 5 in March and May, 7 in November, 8 in December. But then during another time of year when it's a little bit warmer, a bit more, up to 40 millimeters of mercury. That's just 4 centimeters of mercury, which is just less than 2 inches. So don't get too fired up about how much moisture they get. What would you call that? It's definitely not polar. It's not that cold. But it may be the next one down. Humid continental subarctic is what I would guess. It could be humid continental mid-latitudes, but I think that's subarctic. Let's see what they say. Nope, that's polar. I thought it wasn't quite cold enough for polar, but I guess that's polar. Okay? Let's look at example 23.4. Following table lists monthly temperature data and total monthly precipitation data for a city in North America. In which major climate zone is this city located? Notice the temperatures, not a single one negative. Now this is Celsius, so nothing averages below freezing. The average temperature in February, 4.2 Celsius, which would be 35 to 40. Average in February. 4.5 in January, which would be closer to 40 perhaps. 6.5 in December, maybe in the 50s average. And then it gets up to, in July, 26.2 degrees Celsius. Average. So I'm guessing that's probably in the around 80s or so. Okay. Precipitation. Again, this is millimeters. The minimum is 13 in December. That is 1.3 centimeters. So that's about half an inch in December, but a little over half an inch in September. But other than that, pretty reasonable rainfall. What would you think? I'm guessing that's pretty close to where we live. I would say humid subtropical, and that's exactly where we are. Now, it said a city. It could be Birmingham. It could be Atlanta. It could be New Orleans. It could be Tampa, Florida. I mean, it could be any of those places. A bit cool probably for Tampa, but All right. Any questions on major climate zones? Okay. It's a very good map. Okay. Now let's look at local climates. Okay. Now again, climates are the long haul picture, not local weather, but local climates. These range from generally fairly small areas to incredibly small areas. A microclimate is a local pattern in climate. What is happening in a very small thing, and it's been that way for probably a very long time. Now, this could be local climate could be associated with large cities. I think I've already given this example before, but I'll say it again. The heat island or heat dome effect. Now, Birmingham isn't a huge city, but it's big enough that you will notice this. I think you even can notice it a little bit in Bessemer and even smaller cities like that. But I've given this as the example before, and I'll give it again. Especially in the second mini-term, okay? When I'm driving home, my physical science class then will start at 3:15 and go to 7:45 at night. So I'll be driving home around 8 o'clock most evenings. And this will be the latter part of fall, the first part of getting pretty close to winter, but not quite, okay? And we'll be getting some pretty cool weather. So I'll go out to my vehicle, get in the vehicle, and leave to go home. And I'll check the temperature, and let's just make up the temperature. Let's say it's 45 degrees one evening when I'm driving home. Now, I live northeast of here in Southside Birmingham, the Forest Park area. So I get in my vehicle and start heading northeast. Okay, now, I'm not going very far north, and I'm not going very far east in the big picture. But I am going further north and east. Now, north, you would expect, if anything, it should be getting a little cooler, if anything, okay? And if you're going east, you would think, well, the sun's been down longer, not much, a few minutes longer maybe, but if anything, it should be getting cooler, right? And it's getting later at night. I'll leave here, say, at 8. And by the time I get home, it may be 8:30 or 8:45, depending on how traffic is. So you would think it would be getting cooler as I go toward Birmingham. Okay? Let's say I leave the parking lot here at 45 degrees, and when I get out on the interstate and get outside Bessemer, sure enough, the temperature does usually drop a degree or two. Okay? I start heading northeast. But then about the time I reach, say, the Inslee area, suddenly the temperature doesn't drop anymore. It's been pretty stable for a while. It may actually start going up. And then as I get closer and closer to Birmingham, it keeps going up. Malfunction Junction probably is up to 49 or 50 by then, okay? Move on into closer to Birmingham, city center, get on the expressway there, it may even go up another degree or two. Now, when I get off the interstate, Red Mountain Expressway is one usually, and then start heading out in Forest Park, the temperature may stop dropping again, a degree or two. But I usually wind up warmer at home than I was when I left here, okay? Later at night, further north, further east, everything would say, if anything, it should be the same temperature or lower. It's actually a few degrees warmer. And as I was if I went to downtown Birmingham, and I do drive past it, around Malfunction Junction there, it's actually several degrees warmer just about every evening than it is when I leave here. It even is that way now, but it's a lot less noticeable, okay? But in the wintertime, it gets even more, okay? So that's the heat island or heat dome effect. Buildings, pavement, absorb the radiation, the heat in the summertime, in the daytime, and then they don't do anything with it. So they re-emit it in the evening, okay? They emit the solar radiation differently from natural vegetation. And natural vegetation, it's absorbing heat from the sun, it's absorbing light from the sun, but it's doing something with it. It's storing it as chemical energy. So that energy is getting transformed into other kinds, chemical energy, stored chemical energy. So it actually cools the air, if anything. Sure, the shade of the tree makes it feel cooler, but those leaves are actually taking energy out of the air and storing them chemically. Buildings, pavement, not doing that. They absorb it and then re-emit it, okay? So the more natural vegetation and natural light landscapes you have, you can usually moderate your temperatures a little bit. Now I have a niece who has just finished. She's just starting a job in Washington, D.C., been there maybe a month. but she did her master's after she graduated from Auburn in chemical engineering. She went to Scotland and did a year's master's program on smart building design, okay, and clean building and green building design. And one of the things I heard her talk about, and I know a few buildings downtown Birmingham and other places in Birmingham actually, believe it or not, plant vegetation on top of the building. Okay, they have little oases there. One of the restaurants has trees growing on it. This is not in downtown Birmingham, somewhere else. I can't think. It's an Italian place. I can't think of the name. And they actually have that, and that actually helps cool the building. Okay, to have the vegetation on top. So yeah, anything you can do like that will improve in a small way. Okay. Now, these microclimates can even be associated with a single tree. Okay. Big old trees, been there a long time. Sometimes you have one dry side of the tree and a wet side of the tree. The side that receives solar radiation, the side that doesn't. The north side's always in the shade. Okay, never direct sun. So it can. The lichens, the moss grow on one side but not on the other. The north side, they may grow on the dry side, maybe not. The sunny side, moss may grow there, but lichens grow on the, it varies. So you can, there's, any of you into scouting, they teach you how to use trees to help tell you what direction you're facing. And again, that's because of the microclimate around the tree. Okay. Usually the greener stuff's on the south side that gets more sunlight, and the paler type stuff is on the north side where you don't need as much sunshine. All right. Now, here's one place where this author and I tend, I think, not to agree too closely. He doesn't come right out and say it. Oh, okay. Before we move on, there is a blurb on page 594. The concepts applied. Cities change the weather. This is taking what we were just talking about on the last slide and really focusing in on it. So I'll let you read that if you like. Okay, climate change. He doesn't come right out and say it, but there will be a slide that comes really close to saying it. I can tell this guy is not really sold on climate change. I found it really interesting and almost suspicious, because you would think most physical scientists would be able to read and interpret data in a sense a little bit better than what he seems to be doing. But anyway, we'll leave that alone. It says climate change is a departure from the expected average pattern of climate for a region of time, which I think is a very poor way to express this. Time doesn't come in regions, so I don't like the way he phrased it. But anyway, this may have been just the guy who did the graphics. Got that a little strange. Of course, climate changes over time. Everybody agrees with that. Now, this just shows a fairly recent period of time, from year 1000 to 2000. Wait, that's not very recent, you might say. Well, geologically and earth-wise, yeah, that's pretty recent, okay? Because this is just 1,000 years, 1 millennium, okay? And people have existed and stuff, but guess what? We didn't have much data in that 1,000 to, say, 1,500 or so. That's when we first started getting data, and even then it was sort of sparse, and it's only probably been since the 1900s and on that we've gotten really good data, okay? And most recently, very, very good data, okay? So, yeah, it's hard to, you don't see any of this activity here because all we have are smeared averages, okay? That's all you got, okay? So, a lot of the older stuff, they use proxy data, which means something else that tells you is used to infer past climate conditions. For instance, the fossils they get in here, would indicate the type of plants and animals that were growing, and therefore they interpret this must have been the climate that they were in for those plants and animals that existed. So that's what we mean proxy data. It could be the air that's trapped in the glacial ice, okay, that's been accumulating over long, long, long periods of time, and studying that will indicate, in some senses, what the climate may have been like. So it's not really good data. And then certainly before here, way before here, way before there, we don't have a clue, except for fossils and things like this. So he only did 1 millennia here, okay? Now, they know that early on there was a pretty warm period here, okay? Around 1200, 1300 AD, okay? Since then, much of the time that man's been around, well, historically, keeping good records and stuff, we've been in pretty much a cool type period. Now, here's the thing that has most people worried. Look at this. All this is sort of gradual change, taking a long time to get from here to there. That's 300 years to get from here to here. That's gradual. Look at this. From here to there, maybe 50 years. 300 here, 50 there. That's abrupt climate change, okay? In fact, it may be so abrupt you ought to call it weather change, not climate change, but it really is a very steep, not a gradual rise, a very steep rise, and it's still going up, okay? To me, that's unusual. This would be what would be expected, even with this stuff. But that, there's something going on. Well, what has been going on since 1900s? Even beginning a little before 1900s. Industrial Revolution. That's one thing. We have been, back in these times, mostly what they burned was wood, peat, that kind of stuff. Yeah, that was smoky and dirty, but that's all they did. I mean, that's all they burned. Same here, and probably at some point they started using coal, maybe even back here, I don't know. But at some point here around the 1900s, suddenly we discovered mechanization, the steam engine. They were burning first wood, later coal to get our steam engines running. Then they went to electricity, but guess what? Most of that is done by burning fuel oil or coal or something else to run the power plants. Now we're just consuming energy like crazy. Energy that was being stored back here. All the peat, all the plant and animal remains were being stored here, forming coal, forming gas, natural gas, forming petroleum, forming oil, all back here. We're using it up like crazy right now. So all this carbon that was being taken out of the air now is being put back in the air at an incredibly, unprecedentedly rapid pace. Okay? There's got to be something to this. Now, I'm harping probably a bit too much. Let's go to another way to look at this. Data about the ice ages. Now, that goes way before the 1000s, okay? Way before Christ, okay? So way before zero. You're back in the BCs, okay? Data about the ice age and interglacial warming show that periods of warming and cooling occur in large cycles. That's what we saw last time, okay? During the past 100 years, however, Earth has experienced 2 warming cycles. Now look at this. And this may not be unusual. Here was one from, say, 1910 to 1940, a warming. Then it sort of stabilized and cooled a little bit. And then another one since then, from, say, I can't read these. Is that 80? Yeah. 1970 or so until current. A pretty sharp warming trend. Okay? This is just 100 years here. Okay? That 100 years is peanuts. I mean, this is that real steep part that we saw before, or part of it, actually, not even all of it. And this is spread out to make it look like it's not so dramatic, but it is pretty dramatic. That is a huge difference here in just a very short time, in just a number of years. Okay? Sure, there's been these warming and cooling in very large, very slow cycles. Okay? Okay? Temperature changes are not uniform. It says temperatures in the southeastern U.S. have cooled since the early 1970s. Well, this slide was done several years ago. Don't tell me they've cooled much recently. Okay? We have had some hot temperatures. In fact, I would say, I'm just making a guess here, in the last 5 years, I bet you 4 of those have been new record highs. I'm not certain of that, but it seems like I hear that frequently enough. Okay? Sea ice in Antarctica has increased. At least back when he wrote this, or from the data he was looking at from writing this. From what I understand now, it's falling off of Antarctica in record numbers now. So I think his data may be a little old. Okay? But yeah, things happen. They're not uniform. Greenland and the North Pole, the ice is just disappearing really, really rapidly. So yeah, things aren't uniform, but overall, globally, the temperature is rising. Now, here's what he says. The causes of global climate change, they result from a complex interaction of factors. Absolutely. Absolutely. It's not a simple model that you can do. Sunspots certainly do affect climate here on Earth. Sunspots are where these solar flares happen, sending out larger than normal amounts of radiation at times and stuff. But generally that kind of averages over time, okay? What we're seeing, the Earth's tilt, orbital shape, and axis wobble, yeah, that's always happened, and it's still happening. It's not any more extreme now than it was 100 or 300 or 500 or 1,000 years ago. That's always been happening. So, yeah, certain areas of the globe, well, if you think about it, where do we get most of our oil today? Over? Yeah, I know, but what area of the world? Iraq. Okay, Iraq, Saudi Arabia, Iran, oil rich. What are they now? They're deserts, okay, by and large deserts. At one time, that must have been lush rainforest to get all that oil stored under there. So yeah, things change over time. We realize that, okay? And part of that could be due to some of this or other things. Now, here, greenhouse gases. Water vapor, I think more so carbon dioxide, even more so methane, and then other trace gases, okay? Yeah, those are there, and yeah, they've always been there to some extent, but we have been pumping more and more carbon dioxide into the atmosphere since the Industrial Revolution, I think, than any time that's been on record, okay? Methane, can't really speak to that as much, but I bet you we have more of that going out now. You know where a lot of methane producers are? Cattle or other livestock. Okay? We have feeder lots and things like this now that those things are pumping methane. Now, yeah, we've always had huge buffalo herds, but they moved around a lot. They didn't just stay in one place. Of course, they were spreading the methane around, I'm sure, but now we're really concentrating things. Another thing that produces a fair amount of methane are landfills. Okay? They cover them up and they digest the stuff, the trash that we put there, and methane is produced. Okay? We've been drilling. For instance, you've heard about fracking, where they go down and get the natural gas and force it out of rocks and stuff. There's always methane leaks associated with that. There's just leaks they can't control. But if we hadn't drilled, they wouldn't have the leaks there. Okay? Now, another big source of methane are termites. Termite flatulence, in fact. Okay? But guess what? That's not anything new. That's been fairly much constant over time. But a lot of what we're doing today is pumping so much more carbon dioxide, especially methane, to probably a lesser extent, but still to some extent. Now, here's a big one. This hurts us two ways, both ways, all ways. Tropical deforestation. I'm going to pick on Brazil because I've read Indonesia the same thing, I think. What they've been doing, I'll use Brazil, they've gone down and cut down enormous tracts of tropical rainforest. Now, those tropical rainforests typically will pull more carbon dioxide out of the air and store it in the complex carbohydrates like wood, okay? Very complex carbohydrates, and store that carbon there, okay? Well, what do we do? In Brazil has very little oil or hydrocarbon, those kind of things, fossil fuels, you might say. So they are trying their best to supply all their own fuels by growing things, corn, soybeans, and things like that, the oil crops. Well, to do that, they clear the tropical rainforest, which are capturing carbon. They can't do anything with them. They burn them. They burn these huge piles of trees that have been there for centuries, perhaps, long periods of time. Burn them, and now that carbon that's been trapped for over centuries is now going up in smoke into carbon dioxide in the atmosphere. And then they're growing the soybeans and the corn, which, uses some carbon dioxide, but not nearly as much as tropical rainforest. Well, guess what? Those rich tropical soils that have leaf mulch and everything for years and years, decades, millennia, whatever, they farm them for a few years, the tropical environment, they oxidize away, and soon you've got a clay there that will hardly support anything. So they move on and burn some more trees. And now what was a tropical rainforest is barren. It doesn't hold moisture well. It doesn't do anything well. It's a terrible soil after a while. Okay? So we're hurting ourselves big time. The carbon sink becomes a carbon source. Okay? And not a great idea. In Indonesia, they're doing the same thing, but now they're growing palm oil. If you notice on a lot of your foods, when they say oils, a lot of those oils are palm oil. That is one of the cheapest oils to manufacture, and it's one of the worst ones for us to eat, because it doesn't do any good. Corn oil and peanut oil is much better for us health-wise than palm kernel oil, but they just wipe out the rainforest and plant acres and acres and acres of palm oil. Yeah, those are trees that absorb some carbon, but not nearly as much as the rainforest used to. Especially with the fact that they probably burn the rainforest to get them out of the way. Not a good choice. So, here's what he says about global warming. The Intergovernmental Panel on Climate Change, IPCC, which a lot of people say with spit in the mouth, was established by the United Nations in 1988. And it says, here's where I think he lets his true colors show. Despite research, data, and models, the predictions of experts vary. Okay? you would expect that anywhere. In medicine, in anything, the prediction of experts do vary. Not very much, but they do vary, okay? The number of experts that deny climate change, minuscule. But there are some, for sure. And the politicians who want to be climate deniers, they will quote that small number repeatedly and make it seem like they are the majority. They're not. Even among those that think it's going on, that all the data and research show that it's going on, yeah, predictions vary. The models are not good. Just like the weather models. You'll hear James Spann or Jerry Tracy say, well, this model says this and this model says that, you know. Well, yeah, we're going to have the same temperature thing. It's just going to be off by a few degrees, off by a few inches of moisture, rain or not rain. But the thing is, the overall pattern's still going to be there. Yeah, predictions vary, but they're not very much. Okay. Now, here's the part that I really don't like. Critical analysis of climate change should be completed before future policies about human-made carbon dioxide are implemented. Now, it sounds like a pretty reasonable statement, right? When do you complete critical analysis? You're always collecting more data. You're always collecting more information. You're getting better data. You got new equipment, new ways of looking at things, better models, and this kind of stuff. If you wait until you completed everything, I think we'll be dead, okay? Because you just can't put it off forever, okay? Before future policies about human-made carbon dioxide are implemented, if you wait till then, and they really aren't there, it's going to be too late, okay? You're going to be past some point that you probably can't retract, okay? This is not the same thing, but let me just give you an example of what I mean by being too late. West Texas, if you remember that map, that was in the area that was getting very dry, okay? It's been dry. The climate has been dry there for a long, long time. But it's pretty rich soil. It's pretty open land. And they had a pretty good aquifer under it, meaning underground water. We'll talk about that in the next chapter. So what they did, they farmed it. They pumped water out of the ground and irrigated their crops and made some pretty good profits, and continued that and continued that and continued that until they had pumped so much water out of the ground subsided. The aquifers were emptying, and now the soil fell down and filled up the aquifer. Will that ever recharge? If it had been up here, yes, it could. With the soil down here, no, it can't. So if you wait until it happens and then say, oh, yep, it's happening, what do we do now? Guess what, folks? Too late for that one, okay? You're never going to pump the land back up and let the aquifer flow again. It just subsided into it. Same thing here. If we don't do something early enough, it may easily be too late to do it later, okay? Here's another sort of a dumb example of this, but it's fairly, I think, reasonably true, okay? Or appropriate, I'll put it that way. Let's say that I had a jar here. I don't know if anyone knows what a pickle jar is when I say a pickle jar. I don't mean a jar that you buy pickles in, a jar that you make pickles in. My mom had one, a couple of them, I think they were like 3 gallons, big old jar. And she would put the cucumbers in that with the brine, which is really salty water. I think a little bit of alum, which would make crispy, stuff like this. And she soaked them in that for weeks before she pulled them out and mixed them and do the things to make the pickles. That was a pickle jar. So let's just imagine we had this pickle jar. This pickle jar we're going to fill with a perfect medium for growing bacteria. Absolutely everything the bacteria need to live. Okay? So let's say it's got that. And we're going to put a single bacterium in the bottom of that jar. And he's going to find himself in just the happiest place he could ever be. He's going to eat and multiply, and eat and multiply, and eat and multiply. So give me the growth rate that you think that is it. And by the way, because bacteria multiply by dividing. One bacterium divides into 2, 2 divided into 4, 4 divided into 8, that kind of thing. Okay? That's called exponential growth, by the way, by factors of 2. So give me the time period that you think it'll take him to double. So many hours, weeks, days, minutes. Well, with you know what? Just give me, throw out something. Perfect environment for growing bacteria. Make it up.
2 hours.
2 what?
2 hours.
2 hours. 2 hours it's going to double in value. Every 2 hours it's going to double. Okay? Now, give me the time, make up the time that you think it's going to be before that pickle jar is completely filled with bacteria. How long is that going to take? Make up something. 72 hours. Okay? Now, it's going to be completely full in 72 hours. When is it going to be half full? Okay. How about 70 hours? Remember, you said it doubled every 2 hours? It's going to be half full at 70, full to overflowing at 72 in a little bit. What's your window to make a change? To make some decision? You don't have much window. And guess what? We're consuming fossil fuels at an exponential rate. We're pumping carbon dioxide into the air at an exponential rate. Are we going to wait until all the analysis has been completed before we say, oh, maybe we should do something a little different? If we do, we may be past the overflowing part that we don't have time. Here's another sort of dumb example of exponential growth. Have I told this one about the guy who developed chess? Have I told you that before? Story. Okay. The guy who developed chess, now this, I don't know if the whole story is true, but supposedly this came somewhere. So, you know what chess is? It's a regular checkerboard. 8 rows and 8 columns, 8 by 8, 64 squares on the board, right? And it was developed, as far as I know, from some mathematician in India, okay? Way back historically, okay? And India at that time was not one country, India. It was a number of fiefdoms, you might say, various areas controlled by different Maharajis or whatever, And this one very, very wealthy, rich, prosperous area governed by this one guy, that guy fell in love with this game of chess. He said, this is the best thing that ever has happened. I want to reward the person who came up with this. Find out from me who developed this game. So they went out searching around and found in some other province or area somewhere this little housey mathematician who had developed the game of chess. And they picked him up and said, look, the Maharaji wants to meet you. He wants to reward. Oh, no, I'm just having a sweat. No, he wants to see you. It's our order. We got to bring him. So they brought him into his lavish court. Okay? And there the guy said, you're the one that came up with this? This is the best thing since sliced bread. No, he didn't say sliced bread. But anyway, he said something. It's the best thing ever. I want to reward you. Name your reward. Whatever you want. Up to half my kingdom, I'll give to you. Name your reward. He was exaggerating a little bit. He said, oh, Saeed, if it pleases you, that's more than enough reward. No, I get it. Cut the crap. Give me something. Tell me what I can do for you. And he pulled out a checkerboard, the mathematician, and said, well, if you'll put a single grain of rice on the first square and then double it every square after that, that would be enough. He said, are you nuts? That would do a few grains of rice? No, No. That'll do it. Have fleece. That will do it. Okay? Now, in the first row, which is 8 things, that would be doubling, I don't remember the exact number, a few hundred grains of rice. Okay? But before he reached half of the board, he would have emptied every granary in the kingdom. Before you reached the end of the board, he would have exceeded the number of grains of rice ever grown on the planet. Okay? That section is the board. Okay? When do you wait and say, oh wait, no, we just need to study a little longer and make sure that we have all the critical analysis completed before we need to make any decisions about future policies? No. You're going to be past that. You'll empty your granary by then. It's going to be too late. Okay? So I disagree with this guy on this one.
What do you mean it's going to be too late?
Well, things may get so out of control, we have no way of stopping them. And if things, okay, right now, okay, in my lifetime, and I don't even want to say that, in the last decade, how many super powerful destructive hurricanes have we had in North America? Few that were, I can remember maybe a little more than a decade ago, Andrew that hit Florida, and then of course in the same year, which was the one that hit Louisiana, devastating tornado. Hurricane. One that people had to move. They were up on buildings. They were in the Superdome. There you go. Katrina. That same year, Rita hit somewhere in Texas, Galveston or somewhere there, and just was as bad as Katrina was. Okay, and since then we've had the one that smashed into the Northeast and did so much damage there. It seemed like that was an S one. I don't remember that many. Huh? Sandy. That was Sandy. Yeah. And then this year, and last year, wasn't it? We had 3 Category 5s in a row. There was Maria hit, was it that Puerto Rico? I think, yeah, that just really, almost destroyed everything on the island. But that had been just the middle one of 2 other really, really strong storms. And then this year we had this last one. My goodness, I don't think we've had that class of storms in any period that short since they've been recording. That year with Katrina and Rita, they went all the way through the alphabet. They started A, they went through Z, then they just started naming them A, B, B, C, C. That was the next several we had. We've never had that many in a year. Of course, that was that year. But then we've had so many strong ones. So that's happening, okay? Now, we can't say it's all due to global warming, but boy, it sure seems suspicious, okay? So after a while, these storms, wiping out crops, or droughts, they've had record droughts in California and other areas in the U.S. We had a pretty bad drought. You have to actually pick it up and wipe it off your hand. Yeah, that's what I have to do. And so they've had so many things like this. Our whole agricultural system may be messed up. Population's still growing. Energy's still being consumed in record amounts. Okay, think about it. China and India alone are now beginning to drive and consume as much energy, not as we do, but we're beginning to get that way. After a while, the well's going to run dry. And what are we going to do then? What will we do with all the people? Can we feed them? I'm not sure we can. The Green Revolution came along and really increased our capacity, but we haven't had anything like that happen recently. So, it could be really bad. Water, there could easily be water wars. There are already places. Georgia, Alabama, and Florida have been in a dispute for, I think, a decade or longer about the use of water, Georgia using too much water and not letting enough get to Alabama. And we are one of the most water-healthy regions in the country, and yet we're already having a water dispute with Florida and Georgia. Hey, this doesn't compute very well. They have nations in Africa and Asia that are almost at war. India and Pakistan, well, they've almost always had some sort of thing going on, but they almost went to war over water in Punjab. I think it was a Punjabi area. Just because Pakistan decided not to let as much water go down, that was going to starve portions of India and Punjab. So yeah, we don't know exactly how it's going to happen, but things are not going to get any better. And maybe it's too late now, but it's things are getting close to being critical. So I don't know what too late, all the ramifications of it, food, water, temperatures, efforts to keep things cool, it's all a vicious cycle. And if it starts spiraling out of control, it's hard to say how things are going to land. So it's sort of just scary. I think that is the last slide. Okay? That's not quite the end of the chapter. They do show a picture, I wish they had shown it on the text, of sunspots, because they mentioned that. The number of sunspots increase and decrease over an 11-year cycle, and they're indicators that the sun is more active, emitting more energy. But yeah, that's very regular. The stuff we were seeing on that was irregular, okay? They show the orbit of the Earth, and they exaggerate it pretty much, the tilt of the Earth's axis. Yeah, but all that works out, okay? Our use of carbon compounds and pumping more carbon dioxide and methane into the air, that is a little scary. Now, there is one of the best blurbs that I've ever read about El Nino, because I've never heard a good description of it. This comes about the closest on page 597, and it seems like just about every time we get to the Weather Center, Jerry or one of them will mention at least El Nino. So, well worth your effort to read that. You may even see something on a test. I don't remember if, seems like there's at least one question shows up there about El Nino. There is another blurb here, People Behind the Science. This is a little small one. Wilhelm Furman Goran Bergisnes, or something like that. Norwegian scientist who did a lot of the work on he was a geophysicist, okay? And he did a lot of the modeling and stuff like that, weather stations around the world, or throughout Norway anyway, and did a lot of the foundational work of what mostly we talked about in this chapter, the fronts and things like this. He came up with those ideas. Here's what I was talking about with carbon dioxide. This is a graph basically since the beginning of the Industrial Revolution of carbon dioxide emitted or concentrations in the atmosphere since 1860. That was before much of the Industrial Revolution. Look at it. Okay. Unprecedented rise of carbon dioxide concentrations. I don't know if they've ever been that high before. Possibly, I don't know, but they've never grown at that rate before. I almost guarantee you. And to say we aren't influencing, I don't know. I don't see how you can make those claims. Well, that does finish the end of the chapter. You know what I'm going to say next.
Chapter 24 coming up.
Well, yeah, but even before that, nothing replaces reading the chapters, okay? Better to read them before I talk about them, but which by all means read them before you get tested on them, okay? Now, at the end of the chapters is a summary, and this is about maybe normal, maybe a little shorter than normal, but it's a fairly normal summary. Key terms, they go on to the next page, 599 and 600, about the normal number of those. They are listed alphabetically, but they give the page numbers where they're first described or defined. But then, applying the concepts, okay? This chapter has 45, which may be normal to a couple fewer than normal. One of the best tools, I would say, to study for your test. It's multiple choice only. Most of your tests will be multiple choice, okay? Won't be this many questions. It won't be the same questions. But if you know these, you probably are going to be able to deal with the ones on the test. Questions for thought, again, maybe a question or two shorter than normal, only 14 of these, and 4 for further analysis, again, maybe a few fewer than normal. There's an invitation to inquiry, microclimate experiments that you might, if you're interested, choose to do. There's parallel exercises, which a lot of them are kind of forced just to have some exercises to do, but if you're really interested in them, they may be beneficial for your work. So any questions on Chapter 23? So again, the lab for 23 will be the trip to the Weather Center if we can go. Now, last summer, we never got to go. Only term I can think of, at least recently, that we didn't get to go. But hopefully we will work it out for either this Thursday or next Tuesday or Thursday. Okay? Optimal, I think, would be next Tuesday. I'd like to do it this Thursday, but I don't know if he's going to get back to me in time. I'll start calling also, but it's hard to get him. It's really hard to get him. When he's there, he's usually preparing to go online or either they're having their broadcast and you can't talk with them then. And then when he's not there, there's no way I haven't been able to get in touch with him. I have his home number. I try there. I talk with his wife, Kathy. And if I can ever get to her, she's going to get him back in touch with me. But last time I couldn't get in touch with Kathy, so I don't know what was going on. All right. So we will end Chapter 23. No questions? The test will be the last 30 minutes on Thursday, unless the last 30 minutes on Thursday we're going to be at the Weather Center. So other than that, we'll be... All right. Okay. All right, Zachary came in. So let's get started in Chapter 24, if there's no questions on 23. And again, the test on 23 will be the last 30 minutes Thursday, unless we happen to be at the Weather Center then. And then, of course, we wouldn't be able to do it then. But then we'll probably be here earlier, so we could have it before we go. One or the other on Thursday. All right. So let's get set up from current slide, and we'll do this. This is a picture very similar to the one you have in your text. I like this one here a little bit better, I think, but still a picture, and we're talking about the Earth's waters. All right. If you don't realize it, most of the globe is covered with water, okay? Like 60, 70% covered with water, okay? Mostly oceans. The core concept here, which you'll find on 606, the hydrologic cycle. How many cycles have we run into in this course? We had the rock cycle. We had, just all sorts of things that go around, come around, and keep happening. Here we have the hydrologic cycle. Hydrologic meaning? Hydrologic, what does that mean?
Logic?
Yeah?
Any like logic dealing with water or something?
Okay, yeah. Logos means the word or the truth. It's the story of water. That's the water cycle. It's water evaporating from the ocean, transported by air masses, precipitating on land or on water, and then movement back to the ocean. A cycle, a huge cycle. We showed that on a slide in the last chapter when we talked about precipitation. Now, I've seen a fantastic illustration. I don't have it down. I sort of wish I did. A tank of water, a bucket of water, a glass of water, and a thimble of water, and then maybe a drop or two of water, each representing where the water on the planet is, okay? Most of it's in the ocean, okay? The big, big, big chunks. Where would you say the next biggest chunk of water would be?
There were little lakes and rivers.
Actually, in the glaciers.
Oh, yeah, that's right.
Yeah,
Okay,
it's amazing. And we're losing it there rapidly, okay? So it's going into the ocean. The ocean is not potable. You can't drink it. Whereas the glacier water, when it melts, that is quite potable, okay? So, yeah, it's... What's that?
So you could drink glacier water?
Oh, yeah.
Ain't it
It's
full of, like, distinct bacteria from...
not at those temperatures. It will pick up bacteria for sure. Yeah.
We should take it there.
All right. So let's look at water on the earth. Section 24.1. Water is the most abundant chemical compound near the Earth's surface. Now, deep inside the Earth, iron and nickel, yeah, all that's down there. But near the Earth's surface, by far, the most abundant chemical compound near the Earth's surface. Covers 70% of the surface of the Earth. That's more than 2/3 of the surface of the Earth covered with water. 97% of that is in the oceans. 97%. Not potable water, not water you can drink. It's in the ocean. Only 3% is what we call fresh water. And of that 3%, 2/3 of that are in the ice caps, in the glaciers. So that's 2% of the total is in ice cap. Less than 1/3 is available for us to drink. And that would be our rivers, our lakes, our streams, and our underground aquifers. You know, all that added together is less than 1/3 of that 3%. So less than 1%. All right. Now, I think I went too fast. Back off. A hydrologic cycle, which we saw in the earlier thing, evaporates the water from the ocean. The water is transported to other locations. Maybe right back over the ocean again. It precipitates out, returns water either to the ocean directly, which a lot of it does go right back to the ocean. That's sort of a short cycle. Or indirectly. It goes to land. And maybe at land it goes into ice. And maybe in ice it stays there for thousands of years. But ultimately, those glaciers make their way downhill, and at some point they melt and go back to the ocean. Or it falls as rainfall on, not in ice, and then it hits the ground. Now some of that soaks into the ground, goes into our aquifers, and is useful there for quite a while, but ultimately those go to the ocean. Or it falls on the ground, runs off the ground into a river, and goes immediately back to the ocean. One way or another, it's coming back to the ocean, directly or indirectly. It may be in a few years, it may be immediate, it may be decades, it may be millennia, okay? But it's going to make its way back to the ocean. All right, here is the diagram of this. Well, this actually shows it worse than what it said here. The ocean water, it's about the same. No, 97.6%. This is salty, not usable for plants or animals. Okay? Salty water, 97, they say here 97.6. I would round that to 98%. Now, the fresh water, which is 2.4%, here they said 3%. That's generous here. That fresh water locked up with ice, they said here 2/3. It shows here it's better than 3/4 locked up in ice. Okay? After that, In sediments underground, this is what we call groundwater aquifers. That's more than 20%. And then the rivers, streams, lakes, 0.8%, and water vapor in the atmosphere about 0.004%. I mean, minimal, minuscule amount. Okay, all our rivers, streams, lakes here. The underground aquifer, that's a big chunk. Ice is the biggest chunk. After the seawater, salty water. Okay, pretty incredible. Now, here's the hydrologic cycle again. It may not be exact figure that we had on the last chapter, but it's pretty close. In the ocean, the sun hits the ocean, especially near the equatorial regions and stuff like this, evaporates water out of the ocean. Now, the oceans, why are they salty? Because what the water that evaporates out is fresh water. It's not salty water. So the salt concentrations keep building up in the ocean, but they are diluted by that coming in off the land. So they stay about constant, okay? So this is fresh water going up. It goes into the clouds. After a while, the clouds go over. When they get too heavy, they rain. Now, if they rain back in the ocean, that's about 77%, make it back to the ocean directly. But if they make it to land, then about 23% precipitates over the land. Most of it goes back. Look at this, 70%, 30%, 23%. Yeah, just about the same percentage falls on land as falls in, as the surface is covered by. Okay. Now, if that evaporates into the clouds from the ocean, about 84%, evaporating from land, about 16%. So those add to be 100%. And when they say from land, that means from the rivers, from the streams, the lakes, everything, and evaporating directly. And this even includes going out of the trees back into the atmosphere. Okay? Now, so it falls on land, and ultimately, the runoff from the land, about 7%, that falls on the land, that goes back to the ocean immediately. Okay? Ultimately, it all goes back. Now, 100% is based on the global average of 85 centimeters per year precipitation. 85 centimeters be about 30 inches, I think, a year. Is it? Yeah. Something about like that. Okay. Maybe 35, something like that. A lot of areas, a lot less than that. A lot of areas, a bit more. So let's look at the freshwater part. Okay? That little sliver of freshwater that we have. Not very much. Okay? Precipitation is your basic freshwater source. You don't get it much other way except precipitation, falling out of the clouds. Now, of that precipitation that lands on the earth, about 2/3 of it goes right back into the atmosphere. Okay? The remaining 1/3 is what runs off. And that probably is why it's such a small percent here, because more of it goes back up than runs off. Okay. So, 2/3 returns to the atmosphere, remaining 1/3 runoff flowing downhill. Now, if it's deeply downhill, it's not going to do us a lot of good. It just runs right back into the ocean. But, hopefully, a lot of it gets absorbed back into the ground. And that becomes groundwater. That can emerge elsewhere as runoff. We saw that figure in the last chapter, didn't we? Or maybe it's in this chapter, we'll see it. Okay. The runoff, the groundwater distribution depends on the soil type. The sandier the soil, the more gravelly the soil, the more goes into the groundwater. The harder the soil, the more packed the soil is. The clay soils, more of it would run off. Okay. The amount and type of vegetation. Now, this is something we can all contribute to. Okay. just a couple of years ago, my wife decided she didn't want me doing the yard anymore. She said I was getting too old, I was too slow. She wanted me to do other things, so she started hiring some other people to do the yard. Well, I always cut the grass as high as I can get it to go on the lawnmower, because to me, that's healthier for the grass and it's better all along. These guys came in, they scalped it. And now I've got large areas where the soil is running off, the grass isn't growing because they just cut it too short, and the rain runs off. Before, and also when I was doing things this time of year, I started gathering the leaves. The first year we were at our house, I bagged the leaves and we put them on the street. I said, never again. We bought us a chipper shredder vac that we vacuumed up the leaves, shredded them, and then I spread them in the flower beds. So I didn't want a single thing leaving the land. I wanted it all going back into it. Well, they do other things now. I think they do bag some. I tell them not to, but they wind up doing some, but most of it. But still, we're not got as much mulch as we used to. Well, anywhere that you can cover the soil, either with vegetation or with mulch, it holds the moisture better. The more you can do it, the better it holds moisture, and the less runoff you get, the less erosion you get. That's something we can all do, okay? So it depends on the amount and type of vegetation and mulch that you have there. The steepness of the slopes, this is something I did early on. The previous owners, some previous owner, had poured a concrete slab at least 70 feet long and I'd say pretty close to 15 to 20 feet wide on the upper back part of the property, and no one knew why. It encircled a pecan tree, a few other trees, a walnut tree, and it wasn't doing any good for the trees. And I said, why did they do this? I asked our realtor when we were looking at the place. He said, well, I don't know, but some of the neighbors said they thought they wanted their kids to have a place for the swing set that they wouldn't get dirty. And I thought, oh, broken bones are far better than dirty clothes, that, by a long shot. Skint knees, yes, a lot better than dirty clothes. So I don't know. Anyway, we had that concrete slab, except for where we put our utility shed. I had them leave a little bit of that there. But the rest of it had broken up. We had a pretty steep side yard. So what I had them break it up. I said they had a hammer drill on a big old bobcat. I said, try to break it into about 1 foot square pieces. I thought I could handle those. And so what I did, on the places where it was real steep, I built up terraces. And then when we dug out our patios, I filled the soil in behind the terraces. So now the steepness of the slope is not as great. And so we're saving some on runoff there. And then the other thing is the rate of rainfall. I love a nice, slow shower. Okay?
Hot water or cold water, bro? I like mine in cold water because it don't strip the skin of all the water like hot water does.
What?
If you bathe in cold water, it's actually therapeutic. It releases stress off your spine because your spine holds stress on the tooth.
Okay. Yeah, well, I was talking about rainfall.
Rainfall.
Yeah, rainfall. I like nice, okay, not that kind of showers. Okay.
Oh.
In rainfall,
I'm sorry.
in rainfall, a nice slow shower that lasts a long time. If it comes like those thunderstorms and just it's going to run off. It's not going to soak in. So a nice, slow, gradual shower, that's the way I prefer it. Of course, I don't control that at all. The rate of rainfall also determines what the runoff is as opposed to what soaks in. So this sort of shows this. The steeper the slope, the more rapid the runoff. Okay? The more shallow slope, the more it soaks in. Okay? Somewhere down here is where the groundwater lives. Now we'll give names for these areas later. but at some point the stream that's uphill here comes down and actually the groundwater runs into the stream and it all gets carried away. You don't realize this part of it, you realize this part, okay? But that's basically what it looks like. Cover the soil with grass, with trees, shrubs, whatever, mulch, then you decrease the amount of runoff and build up that's going into the groundwater. That to me is preferred. Now, fresh water. Part of it's surface water, the greater part is groundwater. Let's talk about the surface water first. Okay? Collectively, surface water is collectively, the water in streams, ponds, lakes, and reservoirs. Okay? Any water you see on the surface, whether it's flowing or not flowing, sitting there, collecting, whatever, that is your surface water. Now, here's a concept, and we'll be talking about this quite a bit. A watershed is a land area drained by a stream or number of streams, okay? And may form those streams go into creeks, and the creeks may go into rivers. So the watershed is some land area drained by streams, creeks, or rivers. Now, any two adjacent watersheds is separated by what we call a divide. Now, I don't know specifically what the name of this one is, but I've noticed many times when I'm driving down Bessemer Superhighway here toward Birmingham, there's a hill not too far up here. I get to the top of that hill and I can see the whole city of Birmingham. And then from then on, I never see it again because that has to be a divide. The things go this way on this side, this way on the other side. That has to be a divide. That's what we mean by divide. Two adjacent watersheds are always separated by some type of divide. Now, if you look at the entire country, we're split into basically three watersheds. One watershed goes into the Atlantic Ocean, one goes into the Gulf of Mexico, and one goes into the Pacific Ocean. Which of those three watersheds do you think is the biggest? Just make a guess. The one into the Atlantic, the one into the Pacific, or the one into the Gulf of Mexico? Okay, you would think so. It's the biggest ocean. I would say the Gulf of Mexico. This shows it. Okay? Now, this actually splits into a few more than that. Okay? These are the three biggest in the country. The Mississippi-Missouri watershed. The Missouri River comes from Canada. It may be a different name up there. Comes down here, joins the Mississippi here around St. Louis, and then they join together. The Ohio comes in, the Tennessee comes in. All these come in, just tons and tons of rivers, and goes into the Gulf of Mexico. That watershed right there, Mississippi River watershed, is the biggest in the country, and it goes into the Gulf of Mexico in one spot down there. Now, everything over here goes into the Atlantic. Down here goes into the Gulf of Mexico too, just not by way of the Mississippi River. This mostly goes into the Gulf of Mexico. The Rio Grande goes into it. The other rivers go into it, but not through the Gulf of Mexico. Here's the next biggest, or one of these is, I don't know which, Columbia River watershed. That comes from, okay, I'll get back to this in a minute. Comes from this side of the Rocky Mountains and goes into the Columbia River. Lots of rivers rolling into it. The Snake River and several others go into Columbia River watershed. The Colorado River watershed goes down this way. It ultimately goes into the Pacific by the Gulf of California here, or however it goes here, ultimately into the Pacific. All these other rivers don't go in that way, but they still go into the Pacific. Okay? These go into the Pacific. These go into the Atlantic that way. These go into the Gulf this way. So the three biggest watersheds, the Mississippi River, Columbia River, and the Colorado River. Lots of other small ones. Now, what's our divides? Here is the biggest divide. This is called the Continental Divide. This is in the Rocky Mountains, and that continental divide, everywhere west of it flows west. Everything east of it flows east, mostly south. Okay? That's the major continental divide. There's another minor continental divide, that's the Appalachian Mountains. Everything west of that flows into the Gulf of Mexico. Everything east of it flows into the Atlantic. And then, of course, there has to be a divide here between these two, a divide here. Every watershed, like in the state of Georgia, here's the Savannah River, there's the Oconee River, the Mulvey River, there's many rivers flowing into the Atlantic. Every one of those is a little watershed. And there's some ridge in between that's the divide between those individual watersheds. The Chattahoochee River that runs down here later changes its name a time or two. It's the one all the arguments are over, the water wars are over. That flows in between Florida, Alabama, and Georgia here, down to Apalachicola here in Florida. And that's a watershed itself. Okay? It's separated by a divide. Okay? This is a divide. Part of that is the Appalachians, part of it is other divides here. Now, this shows how weird I can be sometimes, if you hadn't noticed. When we were in Yellowstone, Yellowstone is right up here, okay? And this isn't exact right here, but Yellowstone, most of it's in Wyoming, a little bit of it's in Montana. I don't know if any of it's in Idaho. It's awfully close, but not quite. So it's mostly in this corner of Wyoming and Montana, right in there is where Yellowstone National Park is. So this line isn't exact, because in the park, the main way that we've driven through the park, we've crossed the Continental Divide at least 3 times, okay? We go on one side and then the others and then the other, going back and forth over the Continental Divide. So as we went, I'd look down and say, okay, Karen, I think that river is going to the Pacific. This one I think is going to the Gulf of Mexico, because they were. If you're on right crossing the divide, the next water you see is going to the opposite coast, Now, Gulf of Mexico ultimately is going into the Atlantic too, so it's either Atlantic or Pacific. By far, most of it goes into the Atlantic, but a lot goes into the Pacific. But most goes, the biggest watershed is the Mississippi. And it's actually, I like to call it the Missouri-Mississippi, because Missouri comes down here, Mississippi comes down here, then the Ohio comes down here, and then the Tennessee and these others come in here too. So there's lots of major rivers coming into the Mississippi there. Okay. So a divide separates any two, no matter how small the watershed is, separates the two watersheds, and then the biggest ones are the Continental Divide, the one that's in the Rocky Mountains, and the one that's in the Appalachians. This is the major one. The Appalachians is sort of minor, but that separates that going into the Atlantic from that going into the Gulf of Mexico. Okay. Next, after surface water, and by the way, the surface water would be all these rivers, the lakes, the Great Lakes, the other lakes around, the bays, those kinds of things. Not the oceans. The Gulf and the oceans are counted as oceanic water. That's salt water. Okay? But that's your surface water. Now your groundwater is that which soaked into the soil and is down there. Underground water saturating open spaces between rock and soil particles. Okay? It percolates down from the surface. It's 25 times larger supply than the sum total of all your lakes, all your rivers, all your ponds, all your streams, all your reservoirs, everything else. 25 times as much of that is in the groundwater than the surface freshwater. It's often within 100 meters of the surface. Now here is again sort of some sad news. When my father bought the farm down in Georgia, I was 4 years old. My uncle and my father bought it together. Mostly my uncle, but yeah. Anyway, they bought the farm down in Georgia. The house where they we moved into already had a well, but the farm didn't have a well. That was down in Burke County, Georgia. We were in Richmond County living there, about 7 miles from the farm. So my dad commuted to the farm every day to work. So he had a well drilled on the pond. Okay, there were some streams running through the pond, but no well water. So he had a well drilled. And if my memory's right, and I'm not saying it is, it was around 100 to 150, 100 to 125 feet was where they struck good, wonderful, fantastic water. Okay? Really good water. Okay. Now, since then, that well dried up. They drilled another one nearby it, and it wasn't nearly as good a water, but they had to go a lot deeper. Okay? When they built the house, and that was, I got them out of order. When they built the house on the farm, they drilled a well where the house was, and they had to go even deeper than the one over where they were watering the cows. And that was the best water over there. And the one near the house was okay. It wasn't as sweet a water, it wasn't as good, but it was from a different aquifer. Okay? But they had to go, I think, at least 125 feet for that. Then, when my grandmother built a house on the farm, she drilled a well there, and it was about like the other two. You know, not as good a water maybe as the farm, but better than our house. And then the one went out at the shed, so they had to drill the other one. It wasn't nearly as good. They had to go deeper. And since then, my older brother moved a mobile home onto his part of the farm. He drilled a well, and he's fairly close to water. So he didn't have to go quite as deep. He's down in a low spot. Then we were the last well to be drilled there. We had to go. We got down about the 125, 130 feet, thought we had water, but it wouldn't sustain itself. The first thing to do is let it run overnight, make sure it runs all night long. It didn't. So they had to keep going down, and I think he went at least 150 feet, maybe 175, before finally he found good water that was consistent. It is really good water, too, by the way, better than any of the others. Not the old one, but it's just about as good as that. But we're so much deeper. Why? Well, they had several years of drought, that's one thing. But worse than that, there are all these big farms nearby that are irrigating like crazy. And they are pumping water, pumping water, pumping water. And what really irritates me is the fact they spray the water. So in the hot summertime, when they're watering the cotton or whatever they're watering, corn, whatever it is, they spray it up into the air. Most of that water evaporates. That gets to the roots is probably less than, not much more than 50% of what they pump out the ground. So they're just pumping it into the air, basically. And it's just dropping our water table. And if they continue this, after a while, we're all going to have to go deeper and deeper and deeper to get good water. And that irritates me. They say often within 100 meters of the surface. Well, 150 feet is more than a third of the way of this 100 meters. But I sure don't want to go 100 meters down to get it. Okay. Now, how does this groundwater flow? Like it said before, the soil type determines, and if you have a sandy or especially gravelly type soil or stuff that's in the ground there, you have lots of open pore space. Because see, sand and gravel have large particle size, but with a large particle size is also large pore size. And that's very permeable to water flow. It's ideal for water flow. It's fantastic. Demetri, your wallet fell out. On this one? Yeah. All right. Okay. If, however, you have a clayey soil, now I disagree a little bit with this right here. It's not necessarily that it's low porosity. What you have is small pores, micropores. And even though it has just about the same porosity, maybe not as sand, but as a silty or loamy soil, it has almost, and sometimes even more porosity. It's just the pores are so tiny. tiny, tiny little pores. So it becomes almost impermeable, especially when it's saturated and especially when it's compressed. Now, if you compress a clay, then it does have low porosity, because what you've done is wiped out the pores that are there. You press the particles against each other so water doesn't get through. Okay? So part of what he's saying is right, but part of it is just not the best terminology. It's not low porosity, it's small porosity. Okay. Now here's the example I like to give with that. Have you ever gone to a fast food place and got your hot cup of coffee in the morning, and they give you that little swizzle stick that it not only stirs your coffee, but you can, if you want to, sip the coffee through the swizzle stick, right? And that way it helps cool it a little bit. Okay. Now, if you went later in the day and happened to get you a really thick milkshake, would you want to take your swizzle stick and try to suck the, I wouldn't suggest it. You're going to pop your eardrums trying to get it out. It's not going to work. What you need is a straw at least that big, or maybe even larger, and that way you can pull the milkshake up, right? So what you see there, the small opening, it can even be smaller than that, like a pipette, you can't get as much water through as fast, or coffee, or milkshake, or anything else. The larger the pore size, the more your flow. So that's what is happening here. The larger the pore size, then the more the water flows through. Even though you have the same pore size, because it's such small pores, even though you have a lot of them, the water won't go through as fast. It's like sucking through a swizzle stick. Okay? You just can't get as much through. So that's the difference in your soil and your groundwater flow. Okay. And here's an example of that. Here's your sandy or gravelly particles here. Large particle size, but also large pore sizes. So water flows through it really, really, really rapidly. Now here, believe it or not, if you were to add up the pore size here, it's not going to come out that much different from here. It's that the pores are so small, and the water has a hard time finding its way through that tortuous method to get to the bottom. So the water purchase here doesn't run through and it runs off. Here the water soaks through. So this isn't a bad illustration. It's not great either, because the water, some water does make its way down, but it gets stopped. It runs into a boundary here and then has to find another way down. You call that tortuosity. It's torturous for it to get down. Here, no problem. It just flows. Now, this is the way you get water into the groundwater. Very good. If you're trying to grow plants in this, once the rain falls over with, this is dry as a bone, whereas this still has a lot of moisture in it. Okay? But the problem with clay particles, they like to hold on to the moisture too, and they don't release it to the plants either. So that's why you need the humus, which we talked about in the earlier chapter. All right. Any questions? Oh, let me make sure I'm covering everything here. All right, I did miss one thing here. A great blurb on water quality. Okay? I would say most of you probably live, and more than likely have lived most of your life in this general area, right? You know, we have some of the best water around, I think. The Birmingham Water Works has, I don't like the way they operate, but they do have pretty good water. Okay? Have you ever been very much around New Orleans or Tampa, some of these areas near the coast?
I used to live in Texas.
What you say?
I used to live in Texas, and that was different.
Yeah. Good, bad, or worse?
It's worse. And
Yeah.
Temple, my dad lived in Temple, and I used to stay down there for a little while. That water was like salty.
Yeah. So you see, water quality is a big issue. We are very fortunate here to have, I think, really good quality water. I mentioned over at the farm, one well, which is within just a quarter mile of another well, could be just really okay water, but not nearly as good.
And
Depends
Bellsman
on where you
water
take.
is recycled water.
What's that?
Bellsman water is recycled water.
Well,
Because it goes through the water recycle places.
right.
Recycle, I think it's down that way.
Yeah.
So, ain't no drought.
Okay. Guess what, folks? All water is recycled water. There are very few water molecules present today that weren't present thousands of years ago. Okay? And guess what? The odds are, this might sound a little gross to you, the odds are you have up to, okay, a molecule of water is incredibly tiny. You have within your body gazillions of molecules of water, right? The odds are at least one of those molecules of water probably was within, name a person, George Washington, Abraham Lincoln, Genghis Khan, name somebody, more than likely at least one of those molecules may have been in that body at one time, okay? We're all recycled water.
Well, I mean,
Yeah.
Bellsman don't have droughts like other cities.
Oh, I see what you mean, okay. So,
Nah, my side of Bellsman never had a drought. Well, maybe stop saying no. Every time I say no, it's something else happens. So we have not had a drought yet.
Yeah.
My side of Bellsman, 'cause
all right, so that blurb is on water quality. You might actually find the paper topic in there, those of you who haven't done a paper yet. Okay, hint, hint. Okay, there are several questions you can think about and discuss. Okay, then on page 610 was a picture of the watersheds in the U.S., so you'll be visiting that again. There is an example there. And I don't see a lot of reason to put a lot of emphasis on that. And then groundwater, and that's what we're into now. They talk about pore spaces, and they talk about porosity, but what part of the time they talk about is pore size. They're using porosity to mean the same thing. It doesn't. Porosity is the total pore space. Pore size is how big those pores are. Okay. Now we get into groundwater deposits. Okay. Now, how we doing? Okay. Yeah. When water moves into a soil, somewhere under that soil, you're going to hit rock. They call it bedrock, okay? It may be solid, it may be just huge chunk, but at some point, you get to some impermeable layer and the water starts building up on that. That water that builds up on top of whatever your impermeable layer, however deep it is, that is where your zone of saturation begins at the bottom. The collected groundwater above that impermeable layer, that is your zone of saturation. Now, the top of that zone of saturation is what we call the water table, the top boundary of that zone of saturation. It goes down to whatever your impermeable layer is, whether it's rock or clay layer or whatever it is, and then on top of that is your zone of saturation. The top of that is your water table. Okay. The water can move laterally within the zone of saturation. So say water that might be under us here might move as far as Birmingham, Tuscaloosa, or further. It can move laterally within that zone of saturation. Okay. It moves vertically downward to reach the water table and then can move laterally there. An aquifer is a subsurface layer of highly permeable material capable, and this is not a good term here. The material does not produce water, the material contains water, okay? It doesn't produce it, it contains it, okay? Now, believe it or not, there is a huge aquifer under the Sahara Desert. Okay? It seems bizarre, but it is true. Underneath the Sahara Desert is a huge aquifer. However, it's pretty deep, and I'm not sure it would be a wise thing to start pumping it out to water crops on the Sahara Desert. Probably not the best use, but it is. We have, under the state of Georgia, a huge aquifer, or at least it was. Recent year of droughts, more and more farmers have gone to irrigation, and not a smart move. They're pumping that poor old aquifer dry. Okay? Now, one type of aquifer that is really tremendous is what we call our artesian aquifer. The well that we have in Georgia is our artesian well, I think, because it's such good water. I'm pretty sure it's artesian. My older brothers, or at least my sisters, who's at the whole home place, that I think is pretty much surface water, what we call surface water, which all this is. Well, not quite. My parents-in-law had a place up on Smith Lake, and they had a well, and it didn't really go all that deep. That wasn't very good high water quality there. I think that was just lake water that made its way underneath their place, and that's what they were pumping up in the well. We had a neighbor up there. He said his water stank. It just stank. So that had to have been lake water. Okay. So artesian aquifer comes from really, really deep. It's confined under pressure from water at much higher elevations, and sometimes this will produce what they call a flowing well or an artesian well. Okay. Now, near the farm, not on our farm, but near the farm in Georgia, there was an artesian well. It was fantastically good water. It was down near the creek, McBean Creek, and one or 2 years during the Vietnam era, I was in high school. I'm pretty sure it was high school, late junior high, early high school. We were just gotten into Vietnam, or we were in Vietnam, and we found out we were not really very good, especially the Army, at setting up camp in the middle of nowhere and providing for themselves. So the Army needed some places to train, and one of our neighbors, in fact the next neighbor over, he had this big pasture that he wasn't really using that much. He raised beef cattle, but he didn't have enough to cover the whole pasture. The Army wanted to lease it from him, so he said, fantastic, he was going to make more money from that than he would from beef cattle. So he leased that field to them. The field was across the road from our land, and what the Army wanted it for was to put a landing strip in, so that their pilots, the Army has some pilots, could learn to land on rough terrain, build their own airstrip and stuff like this, and it was a hilly area. And I can remember the first night they started, those planes took off at night because they needed to have IFR, is that what they call it, whatever they call it, night ops, and they took off, and their flight pattern that night was right across our house. And every plane that went up, it woke me up. That was the worst night I could remember ever having. After that, I slept through them all, but that first night I was not used to it. But anyway, the soldiers were all out there in this barren field. They were having to bring tanks of water out there to them because there wasn't a well or anything. Well, they found out about this aquifer that was just down the road, less than a mile from where they were, but it was somebody else's property. Well, they got in touch with that somebody else, and they leased that aquifer, that artesian well from them for the time they were there. And boy, the soldiers loved it. The water was so much better than they got out of the tanks that drove down. And in the summertime, that water was around 72 degrees, which felt really cool to drink and really cool to shower with and that kind of stuff. But in the wintertime, that water was 72 degrees because it came from so deep, it never changed its temperature. Okay? It wasn't surface water, it was really deep artesian water. So 72 degrees in the wintertime felt like a pretty warm shower. Not hot, but warm enough that you could tolerate it. Whereas those tanks they brought from Augusta, they were not all that warm. So they appreciated the artesian well that was down there. And they sometimes are called the flowing well. Okay, here's an illustration describing how those things work. Okay, this isn't showing the artesian yet. This is showing the top part of this. You have some impermeable layer here. This could be rock, it could be a dense soil or something like this that the water just doesn't penetrate, or it penetrates awfully slowly. So on top of that, in a more permeable layer, the water builds up, and this is where you have the zone of saturation. Nearly 100% saturated, all your pore size. Now, this follows sort of the same contour as everything else. As some of this water flows into the ocean, you never realize it because it's beneath the level of the ocean. Okay, so you don't realize that. Up here, you have permeable soil on top, but this isn't saturated. But then you hit an area here where there's a deep part, your lake will be there. And sometimes you don't see what's feeding the lake, and you don't see what flows out of the lake, but it's a good, healthy lake. Well, that's because it just happens to be sitting in that saturated zone of saturation. Go downstream a little further, and you can have what they call a spring. This is coming from the saturated. This is not necessarily artesian water. So this would be just saturated groundwater, comes out, and that can flow into a river. And then just about always near, or at least on the East Coast and in the Gulf of Mexico, near your body of water, you'll have low-lying areas that will always be covered with water. It's not because they get that much rainfall, they are in that zone of saturation. These are your swamps, your wetlands, okay? So people talk about draining the swamp, that means you're having to lower your water table. No, we don't want to do that, okay? That was a bad word for that. Okay, which we have a lot of in Washington. Never mind. Okay, I didn't say that, did I? Not out loud. Okay, so that's your groundwater deposits. Now let's move to what we call the artesian wells. Here we have, from somewhere way up high, you have water that goes through all that saturation process and stuff, but then it winds up going downhill, underneath the other soil, and you get down here, and if there is a crevice here, and you reach a well here, because here's your water table. Now, they don't show why that's your water table, but then your well will fill to that water table. And if it's coming from way down here, that's great water, artesian water, almost constant temperature water. Going a little bit further down, and you have another break or something, crevice, something that is, and water has made its way to the surface. This is what they call a flowing well. This is one that you have to dip into and get. This is one that reaches the surface. Now, one of the best swimming areas when we were growing up was a place called Magnolia Park, State Park in Millen, Georgia, and that was based on artesian well. They had an artesian well there. They just directed the flow into the swimming pool. They didn't have to chlorinate it nearly as much as all the others did because the water was always flowing, fresh water always flowing through it. So they didn't have, it wasn't staying there, it was cold. In the summertime, that was cold. Now, when it was really hot outside, that felt awfully good, but you'd come out of that blue looking sometime. So that was fantastic because it was actually from an artesian flowing well that was replenishing that pool that they had there. Okay. The reason it does is this pressure from way up here, way inland, wherever it came from, and that was what was enabling that water to make it to the surface or near the surface. And that's what they had near McBean Creek. All right, now we're moving. We've talked about the different types of fresh water, surface water, groundwater. Most of the fresh water is groundwater, okay? 25 times more groundwater than all the lakes and everything else reservoirs you have on the surface. They have a little concept supplied on deep wells. You can do that if you want to. I don't see that much benefit in it. But now we're talking about fresh water as a resource. I was addressing that a little bit earlier when I talked about the water wars that may be happening either here or elsewhere. Fresh water is required for life processes and modern industrial society. Okay? I've actually heard people make the really dumb comment of, why do we have a water sources shortage? You know, we have all the oceans there. There's plenty of water. Okay? Can you drink ocean water? Yeah, you can, but it doesn't do you any good. It does you harm. Okay? Does anyone know why it does you harm?
Too much salt.
Okay, because it's salty. Well, here's the deal, folks. We are water processors, is what we are. Okay? We drink water. There, Max has a bottle right there. Smart move. We drink water. Goes into us. The reason we have to drink good, fresh, clean water is that we are processing foods and lots of other stuff all the time, and that produces waste within our body. If you've studied your biology, you know there's vacuoles that are in your cells that absorb the, what you might call polluted water, and they get, every now and then, they will fill up so much they squeeze out and it goes into the bloodstream or the vascular system and then gets filtered out in your kidneys, a little bit in the liver, but mostly in the kidneys, and then it gets expelled. Well, now that is not pure water, okay? It is salty water. That is water that has high osmotic potential, okay? Meaning it has lots of stuff dissolved in it. We have to take in fresh water because otherwise there's no place for that polluted water in our body to go, okay? So if we drink salt water, now we're drinking water that's already, quote, polluted. It's already got a high osmotic potential, and our cells can't evacuate because the water that we're taking in is just as bad as that we're trying to expel. So therefore, we die of renal failure because we can't expel the water that we need to. That's why we can't drink salt water. Remember the rhyme of the Ancient Mariner, Samuel Taylor Coleridge? Water, water everywhere, and all the boards that shrink. Water, water everywhere, but not a drop to drink, because he was surrounded by salt water. What was the movie that came out of the pilot in World War II that was shot down, and he and two others, I think, were on a life raft for a long period of time, and one of them, second? I can't hear you.
You said Life of Pi.
No, okay, that was probably a similar movie. I remember when that one came out. This was something like Undefeated or Unconquered or something or other like that.
Unbreakable?
Something maybe like that. I can't remember the exact title. I read the book. The book is fantastic. It is a true story of a person. He was actually an Olympic athlete. Okay, he ran in the 36 Olympics, the ones that were held in Berlin or somewhere in Germany that Hitler was showing off his people. And remember, that's the one that, who's the guy from here in Alabama? Jesse Owens. That Jesse Owens beat so many of their superior race people, you know, the Aryan race. He just stomped them, you know. But anyway, that was the Olympics. And he was an Olympic runner. And then he went into the Army Air Corps, was flying missions, and his plane was shot down, or crashed. I don't know if it was shot down. It may have had a equipment failure. And anyway, he and his I think two others were on a life raft longer than anyone else in history has ever existed on a life raft. And they were ultimately rescued, but unfortunately it was the Japanese that rescued them. And then they were sent to a prison camp, and they were treated really, really badly. But back to the story, one of the guys on the raft basically went mad. And he, I think, just didn't want to live anymore, so he intentionally drank salt water. And of course, he died of renal failure because his body couldn't process out bad water because it had nothing to do. The others were capturing rainfall on whatever they could capture on, and that's what they were surviving on. But he decided to go and actually drink the salt water. And ultimately.
I didn't know some people can drink rainwater.
What's that?
I didn't know some people can drink rainwater.
Oh yeah, I mean anyone could, but he didn't want to live anymore, so he drank salt water, and it hit him out. So anyway, enough of that. Required for life processes and modern industrial society. Now, I was on a U.S. naval ship, and on a ship, you don't, in the old days, back when they were sailing ship, you had to carry all your liquid replenishment in barrels. And anytime you ran low, you had to go into port somewhere and replenish. And that's why they took a lot of water, but they also took a lot of beer, rum, or whatever else, because they didn't have that good of water. Okay. But anyway, that's beside the point. On modern U.S. vessels that are steam-driven, what they have in addition to, your turbines are usually steam turbines. Now, there are a few ships that run on gas turbines, and that's a different story. But most of them are on steam turbines. So basically, you have to make your own water. And they take salt water, and then they have the evaporators. They evaporate the water, and that is one hot job to do, to be in the evaporator room where they're making the fresh water. Because you pump out the sludge, salt water, evaporate the fresh water, condense it, and then pure, it comes out pretty close to pure. Okay, you get a little bit of salt in there, and guess what? The turbines can't use it. The turbines have to have the purest water. So when they say modern industrial society, if anything runs on a steam turbine, which most of our power plants and everything else do, they have to have basically the purest of pure water. So when we were on the ship, the purest of the water went to the turbines. The less pure water, that's what we got to drink. And the least pure, that's what we showered in. And of course, to flush things, that was seawater. We didn't even mess with fresh water there. That was a completely different system. Okay, so the modern industrial society actually requires more water than we do. Okay, better water than we do. Okay, now this is hard to believe. The average U.S. usage, this is U.S., not world, U.S. usage is 570 liters per person per day. Now, what is a liter? A little bit more than a quart. So if you'll take the 570 and divide it by 4, someone do that. It'll be 118 or something like that. 570 divided by 4. No, 100.
442.
Say again?
142. 142.
442?
142.
142 gallons of water a day, each person? No way I drink that much water. I didn't say drink it. Usage. Well, not even a long shower is going to take that much. Now, I can't possibly flush the toilet that many times. So that sounds like way too much water, doesn't it? No, it doesn't. 40% of that is used in agriculture to produce the food I eat. The food I eat, not the water I drink, the food I eat. It takes 40% of that water is for agricultural production. 40% of it is production of electricity. Remember that electricity is from steam turbines. that steam had to be absolutely pure water. Not water out of the water, Birmingham Water Works or Bessemer Water Works or something. It had to be absolutely pure. So they're taking water and the production of electricity, another 40%. 10% industrial. That doesn't leave much that we're actually drinking, because that adds up to 90%. So 10% is then what we use to wash our clothes, wash our dishes, wash our bodies, flush down the toilets, and drink, and that type of thing. That's where our water usage is. If you look at the rest of the world, I don't think there's another country in the world that probably uses much more than half that much. Okay, so we're water hogs. We've just been spoiled rotten because we have so much. My wife's sister and her husband were living in Germany. He was in the army. He was a dentist in the army. They were living on the economy, and they paid dearly for their water. They had monitors in their tub, on the shower, and everywhere else, and they were only allowed a certain amount of water, and they paid very dearly for it. We have it almost free. Not free, but almost. Now, most of the supply that we use comes from surface water. We don't really tap into groundwater that much, okay? Now, the problem with surface water, there's more sediments, there's more bacteria, and there's certainly a lot more pollutants. That artesian water, almost completely pure. Not surface water. It depends so much on precipitation, and I guess that's what Zachary was talking about, that Bessemer, do they actually have groundwater they use? They pump it up, or what?
It's some water that you use for your bathroom.
Okay, so they just recycle their own. Okay.
That's why it has that little chemical-like taste to it.
Yeah. Okay, well, I don't notice it bad around here.
I mean, I'm not saying that it's bad.
Yeah, right.
Just,
I don't even notice the difference.
Don't try out.
Okay. But that, mostly the surface water depends on precipitation. That's why when Lay Lake gets low, Birmingham City goes on water rationing. Okay? So, depends on precipitation. Now, most of that comes from surface water. It says about 40%, or a little more than 40%, comes from groundwater. At the farm, we pump it up, we don't treat it, we don't filter it, we don't do anything. Relatively free of bacteria, relatively free of suspended particles. Now, my older brothers down there near McBean Creek, they get so much sand in theirs they have to filter out the sand and dump it every now and then. But it's almost must be pumped from the surface. So therefore we pay electricity for our water, but that's all we pay. Okay. When you are on city water or surface water, you have to pay for all this purification and for them to pump it to you. But out on the farm, all we pay is electricity to pump it to the surface, which I'm okay with. That's not very expensive. And then we have septic tank, and that's where we planted our blueberry bushes and our pear trees and our other things. So we're hopefully going to recycle that water too. Okay. Now, how are we doing? Whoa! We just went
Over.
Yes. So we're going to pause here, okay, to have a break. I know a few of you have already taken breaks, but all right, the stretch. All right, we're getting folks back now. Let me get you marked. Pi is back, and Demetrius is back. Let's see about the others. Okay, we finished with fresh water. 3% of the water on the planet is fresh, potable water. The other 97% or more, and 70% of the Earth is covered with seawater. Average depth of about 3,800 meters. Average depth, okay? The 30% of the Earth's surface, and Chris is back. The 30% of the Earth's surface that is dry land has an average altitude of only about 830 meters. So if you take the average of all the land and average of all the water, goodness gracious, the water is, what is that? More than 4 times the volume, the depth of water on average than what the height of land is above water. So we're covered with a lot of water, a lot of water. Most of the ocean is still unexplored. Nobody's been there. Remember the old Star Trek thing where no man has gone before? Well, jump into the ocean just about anywhere and you're going to be in places that no man has been before. Most of the ocean is still unexplored. Just minuscule pieces of it have been explored. I'd say a lot of it has been near where the Titanic was, or they thought it was, that's where most of our exploration is usually focused. All right. So we have the oceans and the seas. Now, what's the difference in these? The ocean is a continuous body of salt water that covers large portions of the Earth's surface. Only 3 principal ocean regions. The Atlantic Ocean, which is number 2 in size, the Pacific Ocean, which not only is largest in area, it's deepest in depth. Okay? And then the Indian Ocean is the smallest surface area. Now guess what, team? There's no clear boundaries between these. The closest coming clear boundary is where a continent's in between. But where they actually join, you can't say, oh, this is Atlantic, that's Pacific, or vice versa. Okay? Or this is Pacific, there's India, there's where they end and start. It's just sort of nebulous there. Now what is a sea as opposed to an ocean? A smaller region distinguished by special characteristics. Okay? Now, a sea is still salty water, may not be as salty as the ocean, or it may be, okay? But it doesn't have to be quite as salty, but it isn't potable water. So some of the major ones, the Mediterranean Sea, okay? Large body of water, but it's not big enough to be an ocean. It's surrounded by Europe on the north, Africa on the south, and Asia on the east, which is a little entry there at the where it adjoins the Atlantic Ocean. The Gulf of Mexico is actually more of a sea. We call it a gulf, but it's actually a sea. And it mixes in right with the Caribbean seas. The Gulf of Mexico is bounded by the U.S., Mexico, Central America, and a little bit some of the islands there, stuff. Whereas the Caribbean, South America, and wherever the Gulf of Mexico ends, and on out there. Pretty much identified by the islands that sort of bound it. Okay? And there are many other seas. Okay? Let's see if we can take a look at some. Okay, here are our 3 big oceans. Here's part of the Pacific here, the rest of it over there. They just split it down the middle. Atlantic in here, much smaller than Pacific. And Indian over here, much smaller than either one of those. Okay. Now, don't get too wiped out. This is much bigger here than what it really is, so is that. These are where the globe comes together. They sort of spread it out there, so it makes Antarctica look bigger than any other. It's not, okay? It's just the way it appears. It makes Greenland look bigger than what it is. It's not, okay? Just to give you a for instance there. On the actual globe, Greenland is pretty big. But Greenland here, and this is more realistic on size, looks to be about the same as this part of Canada here, Quebec. Whereas here, Greenland looks bigger than Quebec by a long shot because everything gets spread out here just like it did down here. Because they take this part that's going to nothing here and spread it out and makes it look overly big. That's a projection problem. Okay. Now, those are your three oceans. Your major seas, there's the Mediterranean, the Gulf of Mexico, they don't even identify, Caribbean Sea down here, bounded pretty much by Central America, South America, and these series of islands that are here. Okay, up here is the Bering Sea. Here is the Arctic Sea. Okay. The Black Sea here, the Caspian Sea there, the North Sea they don't label, but it's in here. Here's another Gulf, or is that a bay? I think that's a bay, Hudson Bay. That's Hudson Bay right there. That would be a sea. The South China Sea is right here. Philippine Sea is right here. The Sea of, I can't even read that. Sea of Japan. I thought it was, but it didn't look like Japan. And then there's the Sea of Japan here. Here's a couple of seas around here, around Antarctic. I can't read those here. Waddell is one of them. That's probably this one. And I can't remember the other one. Ross Sea and Waddell Sea. Okay, and that's just a few of them. There's many of these seas, which could be gulfs, could be bays, or main seas. Okay. This shows up in your book. By the way, I haven't turned my page. Back up some. Sorry. I hadn't been turning my pages like I should. There's a closer look on pages 614 and 615. This is before we get into this. It's water quality and wastewater treatment. And this is what Zachary was talking about. This is a good read here. And I would highly recommend you read that. I'm not going to do anything in class about it, but let's see. We still haven't gotten Dante back. Justin came back. I didn't see you when you came in. Demetric came back. I just saw you. That's what reminded me to do this. Ishmael, I think we lost. Looked like he packed up and went home. Darren's not back yet. Zachary's not back yet. Okay. So there's a good blurb there on wastewater treatment. And believe me, folks, all water is recycled water. So don't feel like it's gross or anything. It is. I mean, it's been through many people many times before it got to us. And it'll keep going through people. Okay. In fact, the treatment we do here, like Zachary was saying, Bessemer treats its own and recycles it. A lot of places retreat theirs and then pump them down, let them go back into the river or whatever. And then the next town they capture it and then treat it as fresh water, and it just keeps happening. And that's what the big water wars are with Georgia. Is Georgia has been using way too much of the water and not allowing enough to go on to Alabama and Florida. So you see some of these seas listed on page 618. That's that figure there. A lot easier to read. Okay. Now, what is the nature of seawater? Well, what makes it seawater, we often call it salt water, and that means it has high salinity. Now, every water you drink, now that you've got there, it's probably been purified quite a bit, but I bet you it still has some stuff in it. Yeah. Look at it just a moment. Okay. Purified by reverse osmosis, pure water, perfect taste. Bottled up, okay. Okay, well then, they don't indicate there is anything. Does yours say anything? Okay. Purified water, magnesium sulfate, potassium chloride, that's salt, okay? added a negligible amount of sodium, but the minerals were added for taste, purified by reverse osmosis, just like that. So, frankly, you probably wouldn't like absolutely pure water. Can I see yours, if you don't mind? Purified water, calcium chloride, sodium bicarbonate. Something's been added to make it taste a little better, to give it some taste whatsoever. The calcium carbonate that's in there. They say the sweetest water that you can get is what they call, goodness gracious. That it's been filtered through limestone, which is calcium carbonate. It gives it a sort of a sweet taste. Okay? Seems like they have another name for it. But all water has stuff dissolved in it. Just about all. Okay? Maybe yours didn't, but the others, they added stuff to make it taste a little better. But salinity is the mass of salts dissolved, and this is where they're, this is okay. Mass of salt in grams per kilogram of seawater. Okay? It's the mass of salt, they should say, in grams dissolved per kilogram of seawater. Okay? That means it's a part per 1,000, because there's 1,000 grams in a kilogram. So that means it's one part, how many parts per 1,000? This is incorrect. We'll get to that in a minute. Does not change with changes in water temperature. At least it doesn't change much. Very negligible. The salinity. It can hold more salts at higher temperatures, but it doesn't necessarily change that much. Now this is where they got something wrong. It says it averages 35% with a 32 to 36% range. No! These should be 0 per 0.00. That's parts per 1,000, not parts per 100. See, a percent is per 100. It's not percent, it's per 1,000. So that really, to be correct, and I don't know if your book has it correct, I think it does. This should be, let me get my pen corrected. I'm going to do it in blue because this is in blue. That should be a second zero in the bottom, which is parts per 1,000, whereas percent is parts per 100. Okay? So 35 parts per 1,000, not 35%. A range of 32 to 36 parts per 1,000. Okay? The concentration is increased by evaporation and ice formation, because only water freezes. The salts don't freeze. They may get trapped in there, but they don't freeze. It's decreased by heavy precipitation, okay, ice melting, and river inflow. So some things increase the concentrations of salinity, and some things decrease it, okay? So it maintains about the same. Even though it's always losing it to evaporation, always losing, or some ice formation, but others the ice melt. Now, we were talking about global warming. If our ice melt really increases, which it is increasing, then that can actually lower the salinity of some of our areas of the ocean. That could affect the sea life that's in there, the fishes and other things that live in the sea. That could affect the whole ecosystem. So we don't know where the problem's going to come from, but there's so many. But the precipitation, the salinity is also decreased by heavy precipitation, ice melting. Okay, the proportion of ions relatively constant. They vary a little bit. Now, also to dissolve contains some dissolved gases. Of course, our air is mostly nitrogen and oxygen, so the water near the surface contains oxygen and nitrogen. However, the deeper you go, you get more and more carbon dioxide because more and more fish and other things are breathing in the oxygen and breathing out the carbon dioxide. So you get large amounts of CO2. Now, that's how we get CO2 out of the atmosphere. It comes in through a variety of carbonates and things like that. And this CO2 down deep, it really can build up and then precipitate out and ultimately become limestone. But if you think about it, a lot of your sea creatures like snails and things like this, they take that CO2 out and make shells. Okay, that's mostly calcium carbonate. Your mollusks, have lobsters and everything else have shells. So they trap a lot of CO2. When they die, that builds up, and that then ultimately will become limestone. Okay, that takes the CO2 out, but it can't keep up with what we're putting in now. So here are some of the common ions that are dissolved in salt water. And what do we say? Salt water, salt is sodium chloride. So here's sodium, 30.61, and they say percent by weight. I think here they mean per 1,000 per weight, by weight. Let's see. They say percent here. Oh, no. This is percent of the whole. Okay. This is, of all the materials dissolved in water, this percent, over half of it is chloride. It comes from sodium chloride, potassium chloride, calcium chloride, lots of magnesium chloride. That can come from several of those. Okay, sodium, that's where most of it comes from, and that's a little less than a third. Okay, magnesium, sulfates. Okay, the sulfates could come from sodium sulfate, magnesium sulfate, calcium sulfate, or potassium sulfate. Mostly, I would think, I don't know, hard to say. Magnesium sulfate is called Epsom salts. Calcium sulfate is gypsum. So it could come from either of those. Sodium and potassium sulfates, I'm sure there's some of that as well. Okay, almost 8%. Magnesium, almost 4%. Calcium, surprisingly, is that low, 1.16%. Potassium, 1.1%. Bicarbonate, now here's an error, folks. Okay, this little minus sign here should be up there just like those are up there. Okay, the 3 stays down there, the minus goes up there. So I'm going to try to correct that, but this is not a very good pen to do that with. Okay, I'm going to try to correct it. But like I say, it's not going to be a great pen. This minus sign is not there, it's up here. Okay? No. Okay? So CO3, that's bicarbonate, and it's up there. Oh, here's another error too. Potassium is a +1, not a -1. So that's a plus, not a minus. Okay? Now, I think the rest of them are correct. Bromide is a -1. And that accounts for all but 11 hundredths of a percent. Okay, so that's most of it, folks. All right. And like I said, this carbon dioxide that's dissolved in the water ultimately may be changed and become a bicarbonate. Okay, combine water with CO2 and you get H2CO3, and 1H is an acid ion and this is an alkali ion. Okay. So that's where some of that water, carbon dioxide, may combine with water to be a bicarbonate. Okay. Now let me get my drawing off. Okay. Now, what we mean by this mass of salt dissolved per kilogram of salt water. So 35 grams of salt and 1,000 grams or 1 kilogram of seawater. That would leave 965 grams of pure water and 35 grams of salt. That adds to your 1,000 grams of seawater. So that's what we mean, parts per 1,000. 35 parts per 1,000, not percent. 35 parts per 1,000. Okay. So maybe I should put the zeros back in here too. They were there before. Let's put them back now. An extra 0 there and an extra 0 there. Okay. Now I have to erase those also. Okay. No, they went away. Surprise. So, now let's look at, that was the constituents or the nature of seawater. Contains those salts. There are a couple of examples there. And it's just a game of working with numbers. Okay, so I don't see that that's that much useful to you. All right, before we move to the movement of seawater, let's look at the estuary pollution. Now, I don't know if y'all are familiar with that term estuary, or hopefully you're familiar with pollution. But an estuary is, let's see if they give a definition here, the part of the wide lower course of a river where fresh water in the river mixes with salt water from the ocean is called the coastal estuary. So sometimes you'll hear that called the brackish water. It's not fresh, it's not salt, it's in between. That's your estuary. So that is a good blurb there. I would definitely read that. Now, most of the pollution there is going to come from the freshwater side of it, mixing there. Now, I feel obligated to say this here. It's not going to come up. This author seems to ignore stuff like this. There are huge portions of the ocean that are getting so badly polluted. It's unbelievable. There is some portion in the Pacific, and I don't know where it is, but it seems like it's somewhere about here, that is, you just see mounds of plastic trash. It's just been dumped into the ocean, and it just sort of settles in one area, and hardly anything can live there now. And they don't know exactly why, but they think that some of this plastic breaks down into small bits that look to, say, plankton, like it's their food source. It's shaped the same, it's the same size, and when they consume it, they die. Okay? It's what?
Whales eat plantains.
What is what?
Whales eat the plantains.
Oh, what eats the plankton?
Whales.
Oh, whale, yes, absolutely. It's that, and you're getting right there to it. You see, all the bigger things eat the smaller things. And if the smaller things die out, then the bigger fish don't have their food source. They die out. Okay? And up to whales. And if the whales don't have enough to eat, they could get sick and die. And we have had a few times I've read about recently where unexplained whales just get beached ashore and die. And I wonder if it doesn't come from something like this, that their food source is dwindling or getting polluted themselves. So estuary pollution leads to ocean pollution, and that can lead to some pretty dire consequences. All right, moving on to movement of seawater. Now, this may seem a bit bizarre, but the mixing time for the Earth's seawater, in other words, for every bit of seawater to get mixed with every other bit of seawater, complete mixing happens continuously over about a 2,000-year cycle. Okay, 2 millennia, and then it all gets mixed, and it starts over. Well, it's always mixing. Okay. Now they think it's had about 1.5 million complete mixings over the last 3 billion years. And that's probably been about the time frame that the oceans have been present where they were. We don't know exactly what the nature was before that, but we think the oceans have been there about 3 billion. Okay, 2 types of motion, okay, that contribute to this mixing. One is waves. Waves are pretty much a surface phenomenon. It's not going to go much past a few, we'll see, a little ways down. Produced by disturbance. Most of these disturbances are wind disturbances. Wind moving over the top of the water produces waves. For a long enough time, then it can produce swells. And then that is what mixes the surface part. The deeper parts are mixed by what we call the currents. And it's probably not entirely clear what creates or causes the currents. Part of it is the rotation of the earth. If the earth rotates, some of the water tends to stay where it was, so it makes it seem like it's moving in a current. Okay? But it's movement of water from one place to another. And we'll talk about some other movers of the currents. I don't want to get too far ahead of myself. I tend to do that. So let's first talk about the waves, the surface phenomena. The simplest structure is a moving crest with a moving trough. Okay? Now, here's a picture of that. When a wave is going along, these are really idealized waves. These are called your crests. Okay? Moving crest. And the lowest point, the highest point is called the crest. The lowest point is called the trough. Okay? Like the pig trough, where you feed the animals. Three characteristics that we use to describe these waves. The first is the wave height. That's the height difference between the trough and the crest. That's called the wave height. Vertical distance from trough to crest. The next is also a length measurement, and that's the wave length. That's the distance from crest to crest, or from trough to trough. It'll be the same length, but that's called a wavelength. A horizontal distance, this is the vertical, this is horizontal distance, between two consecutive wave crests. Now that's a length measurement. There's another length measurement we take with the same points, and that's the time measurement. How much time happens from the time this one is here until this one goes there. That's called the wave period. The time between the passage of two successive crests. From this crest to another. See, waves are not just standing there, they couldn't. They're moving, okay? So when this one's here, if you started your stopwatch and kept this in place, by the time that one gets there, that would be your wave period, okay? Or it could be from trough to trough, whichever, okay? But it's a time period. So the wavelength is a distance, wave period is a time. Now, you get a third one from that if you take the wavelength and divide it by the wave period. Length divided by time is speed. That's your wave speed. They don't mention that here, but that's where you get your speed of the traveling wave. Okay? Wavelength divided by wave period. And by the way, there was a figure earlier, and I forgot to mention it. It's in your book at figure 2414. I'll go back to it in the slide set in just a minute. We mentioned that, especially near the surface of water, you have oxygen and nitrogen dissolved in it, because that's from the air. Okay? Well, all water has gas molecules dissolved in it. And I think you see that best when you have ice forming. If you've ever noticed in your trays in the refrigerator, if you have trays in your refrigerator, not many refrigerators have trays anymore, but they used to, that there'll always be a little peak at the top, and there's lots of little bubbles that were trapped in that peak as the ice froze around it. That was the air or gases that were dissolved in the water. And then the bicarbonates are in there as well, and carbon dioxide. There is a rather neat picture of, it says it's the surface of the ocean, but it's pretty close to it. But you see it's pretty calm looking, but even as calm as it seems, there are little ripples and waves that are always. Very seldom is it perfectly flat. Most of the time there's some disturbance has made the waves. And most of the time it's wind. And out in the middle of the ocean, not much else, except a whale coming up and surfacing. I'm going to go back and show the picture that I was just describing before, if I can find it easily. I did notice it here, but didn't think to say anything. Well, maybe I won't see it. There it is. It's at the very beginning. You see the little air bubbles that are formed in here. air that's dissolved in water. Gases dissolved in water. Okay. All right. I think we caught up to where we are now. Now, I can't remember for sure if they're going to show this next figure. If they don't, I'll come back and draw on the previous one. But the ocean waves from the wind, like I said, out in the middle of the ocean, most of your waves are caused by wind. Now, these characteristics of these waves depend on three factors. One was the wind speed. The faster the wind is blowing across the ocean, the more it's picking up water from the ocean, the top surface, and moving it along, creating waves. Now, the wind speed. The length of time that the wind has been blowing. Okay? Now, if the wind has been blowing from the same direction for a long period of time, not only does it produce waves, but it produces what we call swells. Now, the swells will remain there long after the wind changes direction. And we used to record this when we were out at sea. We would say which direction the wind, the waves were coming from, and also which direction the swells were coming from. Swells would indicate the predominant wind. The waves would indicate the local current wind. Okay. And then the third feature is the fetch. That's the distance that that wind has blown across the open ocean. Now that's sort of related to the time here, but also to the distance. The time is how long has the wind been from that same direction. The fetch is the distance that that wind has blown across the open ocean. Okay? And as you can imagine, the fetch in the Pacific can be quite long. Okay? That wind has been moving across the open ocean. Now, what that does for you is produce sort of like resonance. It just keeps piling up the swells bigger and bigger and bigger. Okay. Now, from these three, sometimes working together, sometimes not working together, sometimes working against each other, these factors, you can have a real complicated mixture of wavelengths and heights generated. Like I said, you have waves coming in, which different wavelengths, waves heights, but not only that, you have swells coming in a different direction, from long-term wind. The smaller waves will dissipate from friction within water. Does water have friction? Have you ever done a belly flop into a pool? Yes, it has friction. In fact, the fact that you can swim, you're pushing against the water, and if it didn't have friction, you wouldn't go anywhere. It would just slide right past your hand with no friction. But it does have friction. Okay? So the smaller waves dissipate from friction within the water. The larger waves last longer, they travel faster, and eventually coalesce into a swell. That's what I was talking about. The wind continues from long enough in the same direction, it will produce a swell, and even then the wind changes direction, it'll start doing waves from a different way, but the swells will keep coming from that previous way. Okay? So that's the difference in waves and swells. Swells are long-term waves. Okay. Now, if you've ever been out at sea for very long and been exposed to these elements, you don't want those swells coming in, what we used to call, say, off your quarter from behind. They can just make you really rock the boat badly, okay? Most of the time, ideally, you'd like to be heading into the swell, and that way the whole dynamic of the ship or boat is not going to be as much affected as if they were coming in off a quarter where they could really be rocking you and knocking you about. I remember one time I was on an ammunition ship and we were replenishing another ship, or actually just doing practice runs with it. And the commander of the task force happened to be on the other ship. I don't know if he was an admiral or a very senior captain, but he was some honcho. And he wanted to go in this certain direction, which is not the direction that it should have been going. But he wanted to get back to port soon. So he wanted to be heading to the port. But the swells were coming from our quarter, okay? And that was not the way to do tension rigs. And in the process of doing that, the swell came in and basically almost pushed him into us. And I happened to be the officer of the deck at the time, and the captain was up there too, and the captain just barked out real quickly. We were not supposed to change course, but he barked for us to change course just a little bit, and that drug our stern away from them, and I mean they just barely missed. And they broke the rigs, and the commander of the other ship said, "Good choice, let's go home. You know, that's enough exercise for the day." If we had collided, my captain, their admiral, their captain, possibly me, officer of the deck, would have been we wouldn't have been in that position any longer, you know, because they don't like the ships colliding at sea. That was all because of that other guys wanting to get to port earlier, so he chose a course that was not optimal because it had the swells coming from the wrong side. All right, so here's more about the swells. They carry a lot of the energy of the water that the wind is given, but they don't really transport the water. Okay, the waves actually move water. The swells just basically move up and down without moving water one side or another. Okay, they don't transport water. The individual particle motions are somewhat circular. Okay, now here's the sort of the rule of thumb. The circular particle movement they're talking about here, the diameter of that circle is going to be about the wave height. Remember, from trough to crest. Okay? So let's see this picture. This is the one I was saying. They don't show it. I'm going to have to draw it. Here is your wave height from trough to crest. That's your diameter of your circular motion. Okay? Now, the wavelength, remember, is up here. That's the distance between two crests. If you take this wavelength, take half of it, go that down from your middle point here, equilibrium point, that's how far this mixing occurs. It's all a surface phenomenon. No movement below 1/2 of a wavelength. Here's one wavelength down from your equilibrium point. All your movement is in that first half wavelength. Okay? From the midpoint here to here. The circular motion is that circle here, it's reduced, and below that, no movement at all. So that's why the wave motion is a surface phenomenon. Now, the longer the wavelength, the deeper that mixing goes. But most of the time, the wavelengths are not that long, and so there's very, very little mixing. Okay. So the individual particle motions are circular. Diameter at the surface is one wave height in diameter, but that diminishes as you go down past 1/2 a wavelength, not wave height, one wavelength. You don't have any mixing at all. Okay. From the surface. Okay, what are whitecaps? Whitecaps are formed when the top of the crest, or the swell, it's moving along here, and when the wind's blowing so strongly that it blows the tip over and it foams, that's what is called the whitecaps. It's formed when the top of the swell is toppled by a strong wind. So you usually don't see whitecaps unless you have a pretty big wind, i.e. a storm brewing. So that's how you sort of know when to watch out for rough weather when you start seeing the whitecaps. That means significant wind. Okay? Now, the order of this is sort of bizarre to me, but it makes sense. Okay? When you have these swells or waves coming up to the shore, they get accentuated. Okay? And the reason is, remember that one wavelength depth here? When the bottom of the ocean comes up and starts interfering with that, everything changes. And the top moves faster than the other. So here's shore effects. Okay? And there's a couple of these. One of these is called refraction. What that means is the bending of the wave. The shoreside wave bends, slows down, and the wavefront bends toward the shore. I don't know if they have an adequate picture of that. I don't think they do. This is showing the next part, the breakers, but they don't show the bending. Okay? I'm going to screen ahead a little bit just to see if a later one will. You don't see much bending here either. Okay? So that one doesn't. This one does a little bit. Not much, but a little bit. So you see where the beach goes out here, that means it's probably higher here, the wave gets bent. That's what they mean by refraction, bent toward the shore. The shoreside side of the wave slows down and the wavefront bends toward the shore. So that's not what they're trying to show here, but they do have that picture here. So let's go back here. Okay. Now the breakers at depths less than one half wavelength, or less than one wavelength. Okay. So the half wavelength is where the mixing occurs, but when you're less than one wavelength, which would be twice of these, then things get bent this way a little bit. That's less than the wavelength. The lower part slows down, and the top part breaks forward, and that's why we call it a breaker. Now, part of the reason for that is you see the wind is moving this way, and all the water is getting pushed this way, but guess what? There's nowhere for it to go here, so some of the water comes back. So therefore, the water on the lower side gets pushed out, and the water on the top is still going at the same. So that's why the bending happens. And this is what creates the breaker. That's less than one wavelength, one wave height. I think they've got that backwards. I think that's supposed to be at depths less than one wavelength. Well, certainly at less than one wave height, yeah. The top part, yeah. So maybe that's what they're talking about. Maybe they're not talking about this here. The wave height is here from trough to crest. And when you get less than that, then the water at the lower part slows down. But I think it slows down way before that. So I think they mean, I think that's supposed to be wavelength. Let's see what it says in the book. I hadn't noticed that one before. Okay. Yeah, it's wavelength, not wave height. So let me change that. Okay. At depths less than one wavelength, the lower part slows down, the top part breaks forward. Now what surf is the breaker formation zone. Okay? And you see you don't see a lot of change here, but it's happening underneath. But then when you get up here and the water is being moved back here, the friction with the soil is here, and the waves break over. That's where your surf happens. The surf zone, and the breaker now gets a lip on it. Okay? The surf is the breaker formation zone. Now, the water is transported toward shore by breakers. It has a return, and this creates what we call the undertow. Now, I don't know if y'all have been to the beach enough or ever, And if this is a really windy day and you go too far down here, you can get caught in the undertow and you get pulled out to sea. And you might think you're playing around up here, and all of a sudden you're in over your head. And most of you are probably good swimmers, not a bad idea, but it's still a scary thought. How did that happen? You got in the undertow and got pulled out. Direct return of the water under the breakers. Okay. Now, I don't know if y'all do any body surfing. I used to like to do that, but sometimes if you get into the undertow, you get knocked around a bit, and that's not as much fun as body surfing. Okay. Another shore effect is what they call the longshore currents. That's motion parallel to the shore, and it produces riptides upon entering a channel. And that's what the next feature.
Do we have a test today?
I'm sorry?
Do we have a test today?
I can't hear
Do
you.
we have a test today?
Not today, no.
Okay, because I just got caught in the work. I get me at 5.
Okay.
That's fine. Do we have a lab?
I'm sorry?
Do we have a lab?
Not today.
That's okay.
Not today.
Okay, thing I got to do.
Okay.
My brother gonna take me to work. Yeah.
Okay. All right. Now, I can't think right now what this is meant to show except a nice pretty picture of a beach. Except that you see you got breakers out here, but not here or here. And why would that be? Perhaps you're deeper here, and therefore you're not got the lower friction. And the change of colors here sort of indicate maybe you have got deeper water there. Hard to say without more evidence. Okay? So I guess technically Barron did return, but now it looks like he's leaving again. Zach still hasn't returned, so. All right. All right. So let's get to the longshore currents. That was this one. Okay. What these are is motion parallel to the shore. Now, I know, and remember many times this has happened to me. Now, my wife's family used to go to the beach, it seemed like just about every summer, and then they got to doing maybe every other 2 or 3 summers. Now we hardly ever go anymore. Most of us are old enough that we worry more about skin cancer than we do about playing in the, and we don't really like it. But anyway, I can remember many times going out there and say, body surfing, just messing in the water and stuff like this. Finally get tired and come out and nobody's in sight. I mean, lots of people in sight, but where is everybody? And I thought, wow. I start walking up the beach and I may walk a quarter of a mile to finally see the thing. What's happened? You got in these longshore currents, and you keep playing in it and stuff, but all the time it's pulling you this way. Okay, and that I don't know if you had it happen. Oh,
Just down the beach.
Yeah. You go way down the beach from where you started out, and you never realized you were going there. Okay, so that's your longshore current, and it usually follows sort of that same thing with the beach. Of the waves coming in at an angle and you're slowing down, and that's what creates that longshore current. The motion parallel to the shore produces rip tides, especially if you get to a place where there's a sort of a channel type effect here, and then you can really get pulled out. These can be almost deadly. I mean, they can be deadly. They can really suck you under. Okay. I remember one time I was at Virginia Beach when I was in the Navy. I had gone to visit my cousin and her family, and they wanted to go to the beach, so I went with them to the beach. It was a little bit of a windy day, and we were out there and stuff, and I wasn't a very good swimmer. And in fact, this was on my midshipman cruise, and we were out there, and suddenly I was getting pulled further and further. Like I said, the bottom suddenly wasn't there anymore, and I realized I was getting pulled out. I started trying to swim back, and I felt like for every stroke I went this way, I went 2 strokes back. You know, I wasn't a good swimmer, and my cousin's husband saw that. He was a very good swimmer. And he went and helped pull me along. I don't know what would have happened. I don't want to even think about what would have happened, but it was scary. Because I was doing more and more effort and getting less and less out of it. And that wasn't sustainable. Okay. Before I move too far off this one, at the top of page 623 is a closer look at what they call rogue waves. Unusually large wave that appears with smaller waves. It's also been called sometimes a freak wave, but whatever the name, it's generally one or a group of 2 or 3 waves that are more than twice the size of normal surrounding waves. And you can read about those if you want to. I do know that when you're out there, like body surfing and things like this, now the Gulf is not the greatest place to do it. It's nice, it's fun, but you don't have just lots of activity. The Atlantic is a lot, and then the Pacific, I think, is even stronger, okay, mostly because of the shore contours and stuff. But it almost used to seem like about once every 7 waves you'd have one that'd be a little bit bigger than the others. That wouldn't quite classify it as a rogue wave, but you wanted to get those if you could and ride those in. But everybody else was wanting to do that too, so if you want to be mixed up with everybody else. So anyway, I'll let that go. Now, we're at the place where they're talking about tsunamis. And I can't see this in the book. I looked for it last time, and I do not see where they are, where this is. I think with a subsequent edition, they put that back in the earthquake chapter. Okay? It seems like back there we had something in the book that wasn't on the slide set, and that's the tsunamis. So let's talk about them here. But these are ocean waves created not by wind, but by earthquakes. And just, what was it, this weekend? They had a pretty major earthquake in Indonesia and a tsunami. If I remember, I mean, the death count was in the hundreds, the last I heard. I don't think the earthquake created that much, but the tsunami did. And just all of a sudden, a wall of water many feet high just came ashore. And in a lot of areas, most of the population lives really close to the ocean. Okay? And that was true here, and just out of nowhere. The earthquake had occurred, and tsunami was very quick behind it. They usually have pretty good tsunami warnings in many areas, but this was so quick. And like I said, hundreds of people and homes were basically wiped out. It was really close to the ocean. This can be the largest of the ocean waves. They're not normal. The physical characteristics, now catch this, the speeds approaching 700 kilometers an hour, that would be 420 miles an hour. You got to have some warning to be able to beat something like that, to get ashore in time. You're not going to see it coming and be able to, oh, I better get to high land. No, it's going to catch you before you get there. Okay? Not many things, we don't travel at 420 miles per hour. Okay. The wavelengths up to 200 kilometers. That would be 120 miles. So, but going at 420 miles per hour, it's not going to take long between the first one and the next one. There's going to be more coming after. The wave heights, now out in the deeper ocean, 0.5 meter. That's about a little bit more than this. Okay? No, is that right? Yeah. No. Yeah. That's about 1.5 feet. Okay? That's a little bit less than 0.5 meter. But when you get into shallow water, they grow, okay, up to 8 meters. Now, what's 8 meters? 2 meters. This is 3, 8 meters would be close to a 3-story building. Okay, that part of the A building over there. I don't want to be there. And the 8-meter wall of water comes in. A 3-story wall, building-sized wall of water comes in. Wow, that's going to wipe out a lot of people, a lot of structures, a lot of everything in its path. Okay. Now, also, and here's again, the tides were mentioned back on the Earth-Moon chapter 3. So, produced by Earth-Moon gravitational attractions, already described. The basic pattern, 2 high tides a day and 2 low tides a day, every 24 hours and 50 minutes, okay? So that means there's occasionally you'll have a day that you'll only have 1 high tide but 2 lows, or maybe 2 high tides and 1 low, but it's not going to happen frequently. Most days will be 2 each, okay? Can produce strong reversing tidal currents in narrow bays, okay? Bays that come in at very sharp angles. Then all that water coming in, now it was compressed, so the wave gets much higher. So the strong reversing tidal currents, and this is called the tidal bore, okay? Not like I'm boring, but the tidal is boring, okay? The wave moving rapidly up the bay as the tide rises. Now that's not the crimson tide, by the way. Now, there was a book, I think by Elizabeth Elliot, and the whole plot of this book was this guy lived in an area, guy or gal one, I don't remember now, that had these really strong tidal bores that came in, and this person was swept away in one. And the whole mystery was, did someone take the body out there, or did the person commit suicide? You know? And as far as I can remember, it never was resolved. They had some indication one way and some another, but see, that's a tough one to prove because everything gets wiped out. No tracks, no traces, no nothing. In fact, I don't even think there was a body left. So it was a really interesting mystery. Okay. Oh, Zach did decide to come back today, if only for a moment. Okay. Ishmael did not, and oh yeah, Dante did, but only for a moment. Okay. By the way, Sarah didn't get here today because she has a game, a match, and Stephanie didn't get here today. All right. So this text doesn't have much about tides or tsunamis here. It has them in other places. However, they do produce some pretty significant effects, and that's why the slides are still here, I guess, is they do have significant effects. Did you finish? Okay. Now we're ready to talk about the ocean currents. Okay, this begins on page 624. Okay. Now, what these are, remember the waves produce the surface mixing. The currents produce the deep mixing. These are actually streams transporting water over large oceanic distances along roughly the same path. Just as if you had a river within its banks flowing along there, the current is doing the same thing. Same path, only there's no banks, okay? It's just this stream of water moving in the oceans. Produced by two effects. First of these is density differences in seawater. Now we'll talk about what creates some of those density differences but you do have it. The second is winds blowing persistently in the same direction, persistently, that create these swells that over time, the waves only mix the top, portion, but the swells over a long period of time can then produce these currents. Now, what they didn't mention was the rotation of the Earth, and I think that is sort of mixed up in that one to some extent. Okay? So I don't want to confuse you with it, but that's probably creating something. So, let's first look at density currents. The denser water moves down, displaces the less dense water in deeper basins. So you get the water moving that way, and there's not a lot to keep it from moving in that direction, especially if there's more water coming in behind it, doing the same thing. So soon you have water that's moving. So three things influence the density of water. The first is water temperature. The colder water is more dense, warmer water less dense. So the polar water is much colder and denser than tropical or even temperate water. So the water in the tropics is warmer, less dense. The polar water, much colder, much denser, and this creates currents. Okay? We'll see that coming up in a figure that's probably going to show up here. A second difference is salinity. Okay? The more salt that's in the water, the denser the water is. The less salt, the less dense. Now, the freezing water near the poles makes it even denser. Okay? It's already denser because of temperature, but now that water is coming out and more salts are in it, that gives it more salinity as well. Whereas the evaporation and runoff in warmer pockets, like the Mediterranean Sea, that makes for less dense. So you have flow movement of water upward. Less dense. And then the third is suspended sediments. The more sediments are suspended in the water, the denser it is. These produce what they call turbidity currents to oceanic basins. So you have this messy, cloudy-looking water, high turbidity water that is moving down into the oceanic basins. Okay. Now, here's the picture. And I find this hard to believe. Okay? 65 degrees north. "65 degrees north is right up in here. The Arctic Circle's at 66.5 or something like this. The 65 is right in there. Here's Iceland and there's Greenland, just like we're showing here. Okay? There is this Denmark Strait, and you might wonder, why is it called the Denmark Strait if it's between Greenland and Iceland, where Denmark is over here in the edge of the North Sea and makes the boundary between the North Sea and the Baltic Sea. Okay? Well, because Denmark was the colonizer of Iceland. Okay? So they named the strait the Denmark Strait because that used to be part of Iceland. Okay, so here, cold Arctic water comes down here, deep, dense water, and it goes deep down the side of Iceland into the road. Remember, Iceland's a volcanic island, a mountain. It's not very high up here, but it's very high here. It goes down, and it keeps going down to about 30 degrees north, which is right about here. So this cold, dense Arctic water goes down to here. And guess what it's met by? Antarctic water coming from here that's made its way all the way up to there. Okay? There is some mixing going on there, folks. Cold, dense Arctic water coming in, and actually somewhere running into Antarctic water coming up from way down south, and it's made it here. That's why I found this hard to believe. If this was 30 degrees south, yes, I could buy that. Not 30 degrees north. So they must know what they're talking about. Okay, so that's your temperature differences that create those deep, deep currents of very, very cold water. Okay, even that went over the equator, right? So that's all they say about those currents. Now they're going to talk about surface currents. Okay, now this is what I found a little bit strange. Back here they said two types of currents, density, and then wind blowing persistent in the same direction. I think what they should have said was density currents and surface currents. Yeah, maybe caused by that, but they should have called that surface currents here. There they talked about density currents and gave the illustration. Now they talk about surface currents. These are global circulation patterns maintained basically, and this is what it said on the earlier slide, by patterns of prevailing wind. And believe me, there are prevailing winds. Now, why are the winds prevailing? Because of the rotation of the Earth. Near the equator, the Earth is turning like this. The atmosphere tends to stay in place, so the winds tend to be from east to west. But then up here, because the wind's being dragged in this direction, up here in the temperate regions, now the Earth isn't moving as fast as here because it's smaller diameter here. So therefore, these fast-moving winds that have been dragged in this direction have moved up here, and now they're prevailing westerlies. Okay, so everywhere has some prevailing winds. Okay, and that's what the prevailing winds are. They're also influenced by the rotation of the Earth. There it is. The ocean basin shapes. If you've got underground mountains there and streams through, yeah, that's going to influence these surface currents. And here they're talking about gyres. I think that's how you pronounce it, rather than gyres or however it looks. I think that's pronounced gyres. They're great systems of water circulation centered at the mid-latitudes. That's not real close to the equator, not real close to the poles, basically about where we are, but in the ocean. Great system of water circulation centered in the mid-latitudes. The direction is dictated by the Coriolis effect. Same thing that we have that causes rotation of tornadoes and hurricanes and stuff like that. It happens in the water too, the Coriolis effect. You have currents moving down, maybe temperature or other things, and the spinning of the Earth, it creates these great systems of gyres in the water. The only other place that I can remember seeing the word gyre was in an Alice in Wonderland poem, or it may have been through the Looking Glass poem. Oh, Mimsy were the slithy toes did gyre and gimble in the wave, which makes no sense, except that word is true, gyre. It spun. Okay. Why do I remember that? I'm not sure. Okay. Now, here are a few of those currents. Okay? Now remember, the Earth is spinning in that direction. Okay? So, you have just a whole mix of currents here. Here we have sort of a gyre here, in this direction, this way. You see one down here that's going in this direction. It's northern hemisphere, southern hemisphere. This is clockwise here, counterclockwise there. Here's another counterclockwise down here. Here's a counterclockwise down here. Here's a clockwise up here. So sort of going backwards from what these would be more like high pressure air things. Here's a clockwise up here. Okay? So there are some of these, and they name a bunch of them. Okay? A whole bunch of these. The most famous to me anyway is the Gulf Stream. It's warm, tropical water. Some of it goes and swirls in the Gulf of Mexico. Some of it just goes up. It doesn't even have anything to do with the Gulf of Mexico. goes up and it keeps all of our ports in the whole northern U.S. warm, ice-free in the wintertime. Whereas here's the Labrador current coming down this way, which freezes most of Canada's ports on the east coast. How lucky are we, okay, that we are there where our ports don't get frozen. But this Gulf Stream also makes its way up here and keeps the island of Great Britain, the islands of Great Britain, free of ice too. And that's why she could become the queen of the oceans. She's way up north. She should get frozen. She doesn't because of that Gulf Stream. But unfortunately then, it moves down into the colder waters, and this is just about where those density currents were coming down through thermals, coming down here. This cools off things down here. Now on the west coast, almost the opposite happens because we're on that side of it. See, a lot of these currents are this way. So the cold air from up here around Alaska gets pulled down, and here's San Diego down here, which is a beautiful, warm air temperature, perfect temperature here. You don't want to go into the water there because you have to wear a wetsuit almost all year long. Whereas you'll go in the water and Cape Cod and Atlantic City and anywhere up there and be absolutely pleasant because the Gulf Stream's keeping this warm and the Pacific currents here are keeping San Diego very cool, even in the middle of summer. Okay. But Alaska's lucky because there's another current coming in here that swirls this way and keeps a lot of this southern part of Alaska ice-free, where it shouldn't be. Cool water coming down here, but warm water moving up there. Now, this warm water is probably the same temperature as that cool water, but compared to what it should be, it's quite warm. Up here, of course, everything freezes.
Excuse me, what time is it?
What time?
5:09.
5:09. So we only have about a half hour to go.
Yeah, don't we have to have that test today?
What test is that?
And I thought we were supposed to have like a test on that previous chapter.
I thought we had that.
And I wasn't sure if you was doing that
Okay.
test on 23 or we're waiting on until 11.
No, we just finished 23 today, so the test is going to be Thursday.
All right.
Yeah. We finished 20 the time before. No. We had the test on 20 last time, right?
Yeah.
That was test 7. Because we had finished that before it got started on 23. Then we had that very short class on 23, so we finished 23 today. So yeah, there's unfortunately no test today. No break, I keep talking. Okay. Seemed like I was going to say something else here, but I don't recall what it was now. But you'll be seeing these things again, don't worry. Your lab is going to be looking at this kind of stuff. All right. Now let's look at the ocean floor. Okay. This is section 24.3, which I think, yes, goodness gracious, we're almost finished the chapter. Don't usually do this, but just so we'll have some chapter to do on Thursday or Tuesday, whichever. Oh, man. If we go to the weather station, we will have some time either before or after it, so we'll easily have time to finish this chapter on Thursday. Okay. And then we're going to have our test Thursday. I think there'll be time for that too. And then Tuesday, well, what I'm toying with is whether we should, I could go on and finish the chapter today, but only have test 23 on Thursday and then have test 24 on Tuesday. And then we'll have the final exam on Thursday. But I think we'll have time to finish otherwise too. I guess it's safest to go on and get covered what we can. We're liable to have some fairly short classes for the rest of the time. The trip to the Weather Center is going to take most of one class, and then the other class, whenever that is, either Thursday or Tuesday, is going to be mostly doing the labs and tests. So we don't have a lot left to do, and we've got one short day and one long day to do it in. So what you say we quit today? All right with you? And we'll pick up on the ocean floor next time, whatever next time is. And before we go, though, so at least you'll know, most of the class won't know, but at least you'll know whether we got word from Jerry Tracy or not. If I don't get a response by email, then I'll start calling the station. Last time calling did no good. I still don't see any answer. So I guess I'll start calling. And last time I called and called and called and then finally emailed and he responded. So I said, well, this time I'm going to email, and he's not responding. So, but maybe he'll respond. So watch your announcements and email, and if I hear anything from Jerry, then if it's coming up Thursday, then I'll let you know as soon as I know. If I don't hear anything, or if I hear it's going to be Tuesday of next week, then you probably won't hear from me. Just come to class here. We'll go from there. Okay? So, next time, we'll start with finishing chapter 24. And if we don't not going to the weather station, then we'll have the lab for 24. And then the last 30 minutes, we'll have the test on 23. Okay? If we do go to the television station, then we probably will just finish 24 and go and have the test on 23, and that'll probably be all we do. And then on Tuesday, we'll have the lab on 24, and then probably the test on 24. And then Thursday, we'll have the test on the final exam. Okay? One way or another, we'll get it all in. All right. Good deal. Let me end the recording.